Hello, welcome to the course on additive manufacturing. We all know that manufacturing as an industry has existed for more than 200 years. In fact, industrial manufacturing started about 120 years back in the early 1900s. But before that, even then we had manufacturing, maybe manufacturing of wheels or wagon parts, maybe boxes, house parts, whatever it is, right? But always, when we started manufacturing, we always adopted the same approach to manufacturing, which is called the subtractive manufacturing. Why is it called subtractive manufacturing? Let's say, for example, if you want to make this box. If you want to make this box, this is a gift box made up of plastic or, let's say wood, then what do? We actually take a bigger piece of the material, bigger piece of wood, and start cutting it out or carving the shape that we want, right? And similarly, if you want to make this from metal, then we'll start with a big sheet metal and then start cut out the parts that we want to kind of fold it into this kind of a shape, and then we throw the rest. So in other words, you start with the bigger piece of the material and then either start carving it out, cutting it out, and that's why it is called subtractive manufacturing, because you're taking a bigger piece and you're kind of taking things out of it as a wastage, a scrap, and then you're trying to get the shape that you want. And that's why it's called subtractive manufacturing. However, more recently, there is a new technology concept that is called additive manufacturing, which is fundamentally transforming the way we understood manufacturing. And it is also bringing new price to performance ratio, a new approach to kind of, creating these products or shapes that we want. So in this course, we're going to be spending time to understand the business aspects of additive manufacturing. Our learning objectives in the course will be to understand what is this technology called additive manufacturing, how does it work? Then we will discuss what are some of the manufacturing applications. We'll take some case examples and look at how additive manufacturing is used. And we'll also then go into a framework to understand what are the business advantages, what are the value proposition that this technology brings to manufacturers. And then we'll move on to understanding what is the ecosystem of this additive manufacturing kind of capabilities, and how does an organization build these capabilities? How do they partner with other vendors who play in creating this technology possible for manufacturers? And then we'll move on to understand the primary risks and challenges that are associated with this technology, as with any other technology as well. And then we'll conclude understanding some of the future trends in this technology. In our mode of delivery, of course, there will be video lectures just like what you're seeing now. We will have reflection exercises, case studies, and examples. In addition, we are delighted to share with you that we have some leading industry experts who have decades of experience working on additive manufacturing and implementing the same in large manufacturing companies or enabling this technology to be used by customers. So we have Ashley Eckhoff, who's the senior executive in additive manufacturing at Siemens. Then we have three executives from General Motors. We have Ali Shabir, who is the engineering group manager for industrial additive manufacturing. And then we have Dominic Lentin, who's a group manager for additive manufacturing. Then finally, we have Ron Dahl, who's actually the director of Center for Additive Manufacturing at General Motors. We also have executives from the startup companies or more younger companies in additive manufacturing. We have John Landry, who is the co-founder and chief manufacturing officer as Fast Radius. We just talked about the traditional manufacturing process, which is called subtractive manufacturing, right? Because we take a bigger piece and then we carve it out. But what is additive manufacturing? How does it work? Well, if you want to kind of manufacture or create the same box that we talked about earlier, instead of doing it the traditional way, just imagine if we can build this box layer by layer, right? One layer at a time, kind of every millimeter, and then slowly build this particular material on which this box is built. And suppose if we can layer by layer, we kind of slowly build this shape by printing, one layer at a time and sequentially to create this shape. Then that is called additive manufacturing. Why it's called additive? Because, see, we are not subtracting, we are not wasting any material. We are exactly using the material that is required, and then we are adding material as it is required to form this shape. And that's why it is called additive manufacturing. Now, this concept of additive manufacturing is not that new. Thousands of years back, in fact, it is believed that the Egyptian pyramids were built, one layer at a time. That's how they built these pyramids, one layer by layer to get the shape that they have. Another simple way to connect with this concept of additive manufacturing or additive concept is, we can all recall from our childhood days or where we used to kind of play with something called flip book. You may actually remember where we draw, different layers of the picture that you want to create in different pages, and then you actually flip these pages around, then you see that shape coming up, right? And that gives you an idea how the additive process works. And of course, in this case, you can also, in the flip book, you can also kind of do motion kind of by putting the pictures in different parts, right? So actually, as you play it out, you can see that the layers actually built to make a shape. When you start doing that in a 3D, right, from a flip book, and you start doing it in 3D, what happens is that shapes start building for you to, build this particular box. You can, one layer at a time, you can actually build it in 3-dimensional. That's why, often additive manufacturing and 3D printing are kind of interchangeably used, but I will clarify what exactly the difference is as we move forward. So to recap, we talked about the subtractive manufacturing. What is that? That is a traditional approach to manufacturing where we want to kind of manufacture a particular a shape. Then what we do, we take bulk material, right? And then we kind of start subtracting from the material, whether you're drilling, machining, you're kind of casting, whatever you want to do, you're actually cutting it out, right? You're taking out the additional material that is not needed to arrive at this product or the shape that you really need. So when you arrive at the shape that you really need, of course you are left with what? You're left with a lot of waste. And in a traditional industrial manufacturing, we call that scrap, right? I mean, if you have, imagine, kind of a recall walking through any manufacturing plant, whether they are doing any parts or any shapes they are creating, you'd see that there'll be a lot of scrap. In fact, the scrap that comes out of manufacturing is the wastage, right? In terms of, just creating this particular box, we may think about, well, I would actually come some plastic pieces, some wood pieces that I don't need, that I'll throw it away. That's how we think about it. But in an industrial manufacturing setup, that scrap is a huge issue because, you'll see that in these manufacturing, places, the scrap comes out so much because it's volume in manufacturing, right? And then the scrap is then hauled in trucks to a separate scrap yard where they sometimes may melt that metal or do something with that resin, plastic. So whatever they need to do with the scrap. So what I want to say is that this is an enormous process that takes a lot of resources and time because you're creating wastage and that needs to be processed, that needs to be recycled or whatever needs to be done. But that is your subtractive manufacturing. Now let's look at additive manufacturing, right? If the same shape you want to create in additive manufacturing, you would start with the materials, okay? Because the material may not be in blocks. You need to kind of create the material in metal powders or plastic, polymers that can be melted and things like that. Then through a kind of a printing jet, you start printing layer by layer the shape that you want. When you start printing it layer by layer, that is the additive manufacturing, right? Then you get the product and the shape that you want. There is some scrap and some wastage, not much at all. I mean, nothing as compared to what you see in the traditional manufacturing. So this is the process of, creating a shape or a product through additive manufacturing. And you can see you're printing it in 3-dimensional. That's why it is also called 3D printing. And this concept of 3D printing is very, very popular now. In fact, you might have heard about concepts like you can actually get your shoe 3D printed, or you can, print toys. And what I call those are consumer additive manufacturing or consumer 3D printing, right? Where in today's world, we can, there are cloud companies where actually kind of if you want a bottle to be 3D printed, you can actually kind of go to one of these companies, you design this bottle on a digital design of this bottle, then you pick the material, you want plastic, you want some other polymer, and then you just pick the material and then send the file to them. They would print it for a price and send it to you. So that is consumer 3D printing or consumer additive manufacturing. But in this course, we're not interested in the consumer side because that doesn't scale. It's more for fun and different usages. But we're going to be focusing on industrial additive manufacturing, how this concept of 3D printing in the industrial manufacturing is fundamentally changing how we understood manufacturing, what are the new capabilities it is bringing. Also, it is challenging some of the basic assumptions around manufacturing as we understood the last 120 years. So the concept of additive manufacturing, we can create complex products, simple products, as shown in the picture here. You can see that, top one is a very simple box, easy to kind of comprehend, understand. Whereas the one below is, complex box with different shapes and kind of cavities and holes in them. So you can see that different kinds of parts are possible. Now, how do we do this? Let's understand what is this additive manufacturing process. Well, often you might have heard that the term 3D printing and additive manufacturing, they're actually, often used interchangeably. The reason is, 3D printing, as the name suggests, it actually focuses on the verb, the action of printing, because all these parts in additive manufacturing are printed layer by layer, as we discussed. And that's why that particular printing part is 3D. It's called 3D printing. However, additive manufacturing is a broader concept, which is a kind of an umbrella concept, which is a transformative approach in various stages of manufacturing, in design, in the manufacturing, in quality inspection, and also in customer engagement. And this process of making object in additive manufacturing is actually layering of materials. The materials could be metal, polymer, plastic, and there are so many different, ceramics is also possible. There's so many different materials are possible. Then this particular technology actually is also a capability for improving the performance of parts, right? Because it actually, on the design side, additive manufacturing starts with, digitization of the design and working out different combinations. And that process can actually lead to a capability for, improving the strength of the part that is being developed through design changes. They can actually reduce weight, improve the cost, and also, handle complexity completely in a different way. This technology uses computer-aided design, CAD, it's called CAD software, and more modeling and simulation on those computer-aided design software to kind of play around with the digital design of that particular product. Like if you want to kind of print that complex product on the right, you start with the design, and then you kind of look at multiple combinations. In fact, more and more what's happening is that you have software-controlled algorithms exploring different design options and then coming out with the optimal design. And then that particular design, when it is finalized as a digital design file, is actually sent to these printers, or we use 3D scanners to kind of capture a particular design from an existing product. And once you have a digital file, then that is sent to the printers to deposit material layer by layer by using different techniques. And that's exactly how the additive manufacturing process works. Again, it is a process that actually includes the design phase, the manufacturing printing stage, and also it has implications for quality and inspection as well. So what are the different steps in additive manufacturing? To recap, you start with the digital file, with digital design file. You look at modeling, simulation to look at the various options. You optimize the design. You may actually take an existing product and improve the design as well if you want to kind of use additive manufacturing to improve the performance. Then from there you come to a printable file, and that file is then transferred to the additive manufacturing machine, which is called the 3D printers. And the machine needs to be set up, and then the machine starts building. Building is what then it is printing this particular part one layer at a time. Then, of course, you remove the part. You may have some scratch to kind of take it off, and then you do some post-processing on that part. You may do some post-processing on the part, and those are the kind of steps that takes to complete, using additive manufacturing to create a part. Today, we have Ashley Kopp from the Additive Manufacturing Group at Siemens. Ashley, welcome to the show.
My pleasure.
I would like to first start, asking you, Ashley, based on your, you've been in the additive manufacturing field for many years now. How would you explain this process of additive manufacturing, or what we call is 3D printing? Very, very layman terms. What exactly is this technology?
Well, before we talk about additive, we should probably talk about traditional manufacturing methods and how they work. traditionally, the way a product is manufactured, be it parts for an automobile or even something like a toothbrush, they use some very well set manufacturing methods like machining or injection molding. So with machining, you're taking a big block of material. This is the way a lot of car parts are made, and you're basically shaving off all the parts of that material you don't need to get to the shape you do need. Injection molding is a little different. With injection molding, you have a cavity and you're filling that with a material to basically manufacture the part you need in the end. Additive works differently than both of those. You can think of additive manufacturing almost like if you've ever had, when you were a kid, a flip book where it's a bunch of images stacked on top of one another and you could flip through those to make an animation. Additive is very similar. You're producing a part, but you're doing it layer upon layer upon layer. So it's basically stacking a bunch of sheets of paper together that are cut out in the shape you want to make, if that's a really simple way to talk about it. But that's basically what you're doing, a layer by layer building of whatever shape you want to have in the end.
Now, in order to kind of better understand, the benefits or how additive manufacturing works, let's take some couple of industry examples, okay, to make the point like why this particular technology is very important and beginning to get some traction. Well, this is kind of a burner, from the energy industry that Siemens had worked on. At one of their customers, and basically you understand there's a burner, there's a kind of you can see there's a burner pipe that's going inside, and there are different parts. On the left hand side in this picture, what you see is the traditional part as it was, the burner as it was, right? And this traditional burner had 13 parts which are joined together, and it took them 26 weeks to design this entire set of parts and then put it together to kind of create the burner. And of course, it was weighing about 4.5 kilograms when they finalized the design. So that's the design side of it, where they have different pieces, and they've designed each one of them, and they've actually found out, how those will be put together. And that's the lead time for design it took, and then that's the weight of the product. Now, you also understand the manufacturing piece, right? If you want to manufacture this particular burner, then you have these 13 parts. Each of those parts will be manufactured, separately, but doing different kind of techniques, injection molding or casting, whatever it is, depending upon the material. And so you make all these 13 parts, and there is a mini assembly process to put this burner together, right? There's also an assembly process to kind of get all these inventory of these parts and putting it together. Now, that is the traditional manufacturing process. You see, you have 13 parts that are joined together to form this burner, right? And then you have a long lead time, and then you have this complex set of manufacturing these 13 parts and assembly stage of putting this together. On the right-hand side, what you see is that how Siemens completely transformed that particular product by totally designing it in using additive manufacturing tools, right? So using additive manufacturing, they actually took the design back into the kind of design software, looked at optimizing the design, and capturing the functionality that is required in the burner, and then they actually combined it into what I call as a complex or a compound part, which has got multiple parts together, and to convert it into one part. So those 13 parts that you see on the left in the traditional manufacturing has been converted into now just one part that you see on the right, and that will be 3D printed. It will be through additive manufacturing. You just you have the design, you optimize the design, you actually print that part, and look at some of the metrics there. It is now your 13 parts has become one part. That means you don't need any assembly at all, and your lead time has now come down from 26 weeks to 3 weeks, and your weight of the product has come down from 4.5 kilograms to 3.5 kilograms. That's a 1 kg reduction, right? That's going to have cost implications, reduction in cost. Of course, it's also going to make the planet more greener and things like that. That's one example. Let's look at second example. This is from the aerospace industry. This is a part that goes into the airplane seats. What you see on the left-hand side is the original part, right? The original part that is the connector in the seat. And the volume of this part, how big it looked, was cubic millimeters that you see. and the mass, weight of the part was about 2.06 kilograms. Now that part, they actually took it to additive manufacturing and then kind of looked at the design, and through design optimization, simulation, and various kinds of optimization, they actually they use techniques like lattice optimization, which looks at the structure and then brings the same strength or improved strength, but with a different structure. So kind of all those simulations and modeling with the design tools and intelligent algorithms came out with this design that you see on the lower part, which is the kind of design that came out of the additive manufacturing process. And then this particular part was 3D printed, and now you see the topology of that particular part has changed. The shape of that part, structure of that part has changed, and you see the volume is reduced a little bit, and then the weight is actually, the mass is significantly reduced, right? And again, this tells you the strength of the material is almost the same, it's not better. And then you have kind of saved in terms of the material that is, how much material that is required, and also the weight of the kind of this particular part. And contextually in the aircraft industry, as you can imagine, even a single kilogram reduction of a particular part, brings down the weight of the entire aircraft, is it not? And that saves them thousands of dollars. So that's where now you're beginning to see the business implications of why additive manufacturing is very important, is catching up in terms of widespread usage, at least being tested out significantly. The technology is still emerging, but it is being adopted quite rapidly in the last few years. So let's understand, looking at these two examples, what are the broad advantages of additive manufacturing? As I mentioned, additive manufacturing is an umbrella term, and the advantages can be seen at the design stage, at the manufacturing stage, and also in the quality inspection and testing stage. So on the design side, as we talked about, the digital design allows the manufacturers to optimize to come out with the best design that is possible, as you saw in the burner example. And you can also come out with the new design. You can change the design of the part, the structure of the part, to improve the weight or efficiency. And so virtual simulations in the software allows them to use machine learning algorithms, intelligence to look at new design space and new design options. On the manufacturing, what additive manufacturing brings is just-in-time manufacturing. You can just print the part when you need it, where you need it, right? You could actually we are not there as yet, but there is a potential capability that you could actually print the part in the last mile, where exactly you want it. Suppose I have a factory in Chicago and then have a customer in San Francisco. You don't have to manufacture it in the plant here and then ship it through logistics, but you can actually directly print it in San Francisco. And of course, that's what I call about the capability for distributed manufacturing. That has a lot of implications. We'll talk more about it in the course. And then, of course, you see automatically reduction in inventory and scrap. We talked about that before, right? That's a significant change in manufacturing productivity. And you also begin to see consistency in quality. Because a lot of times all the lean processes, Six Sigma terms that we all know about manufacturing, and it's all about reducing the variance, right? But in the concept of 3D printing, if you have the same file and the same printer, you can consistently print the part. So that means by design, there is consistency built in, and that has a lot of implications for quality as well. Now, coming to quality, right? You can build real-time quality inspection. In traditional manufacturing, you would actually go through the process of manufacturing the part, and then there is a quality stage where actually people inspect. Whereas, in 3D printing and additive manufacturing, there are capabilities where you can real-time, through inspection of the material as is being printed, you can automatically inspect for quality as well. So in some sense, there is an automation of quality control that is built in. But at the same time, additive manufacturing also brings in some trade-off. It is, as I said, it's an emerging technology. It is not fully ready to be used because it comes with some trade-offs, right? And first, the cost and speed of manufacturing. We'll talk a little bit more about the economics of this technology later, but I just want to mention that additive manufacturing could be expensive, and the speed is another kind of a challenge here. because especially, for example, if you take the example of Ford Motor Company, which is, I think the statistics are supposed, one of their popular products, the Ford F-150 truck, they manufacture about one truck every 43 seconds or something like that, I read. But that's the speed of your manufacturing. Scale manufacturing, then additive manufacturing or 3D printing is not ready for that kind of an application, because the process of layer by layer printing does take time. Because what you could do in a traditional injection molding, say in hardly half a minute or something like that, may take 20 minutes or 30 minutes in additive manufacturing. So that's not feasible. That's one trade-off. Then there is scale of manufacturing that actually, you're not ready with additive manufacturing because of the speed issue. You can't scale in large number of units in short time. Also, additive manufacturing, can be expensive, and so we look at opportunities where the customer is willing to pay a premium price for the improved design of the product, right? For example, a significant improvement in that aircraft, seat part, right? We just talked about. That makes a lot of sense. Aircraft industry will pay the premium price because we talked about the business implication for them. Whereas on the same token, it may not make sense business wise for using additive manufacturing to 3D print a radio knob in a popular car, which is manufactured say in millions of units in a year. Size of the part is also another trade-off, because the additive manufacturing process by design now is kind of limited by maybe 2 feet by 2 feet or something like that. That's the normal size, beyond which it becomes a challenge. There are concepts and experiments going on where people are talking about printing the entire frame of a vehicle and things like that, but they are in the experimentation stage. They are not for mass production as yet. So in summary, in this section, we talked about what is additive manufacturing, how is it different from subtractive manufacturing or traditional manufacturing. Then we looked at the difference between additive manufacturing as a term and 3D printing, why they are used interchangeably. We looked at broad advantages of additive manufacturing concept in design, in manufacturing, and testing. We use some industry examples, especially the burner example from the energy industry, where we combine 13 parts, right? Siemens was able to combine 13 parts into one part, hence reducing significant resources in manufacturing and also design improvement. And we also looked at the other example of a part that is used in the airplane seats, which through additive manufacturing, they could improve the structure through design optimizations, and hence reducing the weight of the part and making significant business benefits for the aircraft manufacturers. And finally, we also touched upon some of the trade-offs of this technology, and right now why this technology is not used in mass production, but but still has a lot of capabilities, and there are specific situations where it is used. And we concluded, understanding both the advantages and the trade-offs in this technology. We just learned about the broader process of additive manufacturing. I looked at examples of specific parts, and also we discussed some trade-offs in additive manufacturing. Now, let's go and see what are the general applications of additive manufacturing. How do manufacturers use this technology right now as this technology is emerging? And it has got a lot of promises. And so when you see how this is being used in the manufacturing, I would actually categorize it broadly in three categories. First is on your left-hand side is the tool development. Because tool development per se, actually kind of meets some of the criteria we talked about, that you need for additive manufacturing, right? Because often the manufacturing, by tool development, I mean the manufacturing tools that are used in the production process, right? And those tools usually are not made in millions and large scale. So they are low volume products, low volume parts. And so they are suited for, additive manufacturing and 3D printing. And in the tool development area, what this technology brings in is actually it improves the cycle time for design and production. If you want to design a quick new tool and then you don't want to be spending weeks and months, waiting for the tool to come in, because then that actually, is delaying the production process, right? So this capability for, rapid tool development and improved cycle time for changing design tools, that's a big advantage. And of course, also reduce cost of tool production, as we saw in some of the, additive manufacturing techniques. You could use, sometimes you could take the same tool and redesign the tool, with a different material, and actually it can bring down the cost. Sometimes it will, improve the performance of the tool as well. And also the third bullet point there is, you could actually optimize the ergonomics and performance, right? And, how the tool is designed, how the tool is used in the manufacturing process, it can have, impact on the people who are working on the manufacturing floor, in the, how they are using it and what kind of, which muscles or what body parts are using to kind of, to apply the tool. So that could be, studied in detail. The design could be worked out, because, in additive manufacturing, you're working with the digital design to kind of look at different combinations. You could improve the design to hence optimize the ergonomics of the tool as well. So here is an example of, additive manufacturing application in tool development. This is an example, thanks to General Motors for sharing this with us. And this is a tool that is used in, assembly body quality. And you can see that the tool was, they had initially one tool, and then they actually used additive manufacturing and to design that tool and then print it, use 3D printing, and to create the tool, as you can see. And also on the right-hand side, you can see how the tool is being used by the worker on the shop floor. In this process, they were able to reduce the weight of the tool by 84%, right? And that has significant implication. Think about it, that the factory worker on the right-hand side, they are actually using this tool in their hands, and then to kind of, and if their weight is reduced by 84%, that has significant implications for ergonomics and, the impact on the worker. And they also were able to reduce the cost by 91%. And the last one, even more important, is the lead time reduction for creating this tool from 14 weeks to 4 weeks. And that's the order of benefit that they're getting. And you can see that why additive manufacturing is such an important technology, and it is fundamentally, changing the price performance and, cost equation, cycle time, all these business benefits that we'll talk about later. So that's one example on the tool development side. Now, coming back to the second category of how, applications in additive manufacturing, how companies are using this technology, is what I call as rapid prototyping, right? Often when companies are faced with changing a particular part or improve the design of the part, they would like to build prototypes, and they would like to look at various options. And they certainly, when they're doing that prototyping, they would like this process to be faster, because prototyping often involves iterations by changes and see the impact of that change. So additive manufacturing, with again the digital design and the capacity to model the design and then do a lot of simulations, use intelligent algorithms to look at different options, and it leads to the faster iteration of for performance improvement of the particular product, or the part. And it also improves, it brings the capability of real-time quality checks, like if you use additive manufacturing as the part is being printed, then you can actually look at quality issues as it is being printed. And of course, it can also reduce the cost of change orders. Often what happens is, when you want to kind of put a change to a particular part, and that in a manufacturing large automobile or aircraft manufacturing context, that could be very expensive, because any change order that leads to a particular part change in the part, then they have to build prototype, they have to iterate and test it, and they have to go through so many stage gates to kind of make it happen. But additive manufacturing can significantly cut down the cycle time, end-to-end cycle time, and hence lead to rapid prototyping. Here is an example again from General Motors. If you kind of remember in the one of their popular products, Chevy Corvette, there is this at the front of the car. You can see this this part, which they call as the brake cooling ducts. It is right below the headlights there. You can see these ducts are actually kind of sucking in the cool air that comes in, and then redirecting that air to the brakes so that the brakes are cooled. And that particular part, and they had the initial part, and they actually kind of redesigned that part and then used additive manufacturing, as a technology to improve the parts. And that process actually allowed them to make 4 design changes at no cost. They could actually change the design change and then iterate it, because it's all in software, in digital design, and then that actually almost cost them nothing. And overall, in the cost of the part, they achieved 64% cost reduction. And then they also had 0 parts failed in testing. When they tested the part, there's no failing at all, because as I said, this is one of the kind of in 3D printing and additive manufacturing, if you get the process right, then the consistency often is by design. And finally, and then the last but not least, in fact, one of the most important dimension is the reduction in the development time. That's why it's called rapid prototyping. They actually reduce the development time from 10 weeks to 1 week. That's order of 10 improvement, and that's big benefit in terms of overall reducing the overall cycle time of new product development or any design changes to any part. Now, coming to the third category, what I call as industrial production, 3D printing is not there as yet in terms of there are so many parts. It doesn't cost-wise make economically viable for us to 3D print the part, but still it is being used in industrial production as well. But as I saw in the example of the burner in the energy industry, when you consolidate parts, right? When you're able to consolidate parts into one single part, then even though 3D printing may be expensive, it is still viable, because you're now saving cost and productivity and time. Where in the case, if you recall the burner example, you had 13 parts. You had to kind of manufacture, produce each one of them, combine them, assembly, test each one of them, test the assembly, all those things. You're reducing all those resources and time, and that's why cost-wise it may become viable. And in industrial production, the additive manufacturing is used for discovering new designs. And more importantly, the concept of additive manufacturing, as we have now understood. Now you can recall back when I introduced this series, this course series, I talked about the broad big changes that are happening in the manufacturing industry. More and more manufacturing customers are asking for personalization. They want a personalized experience. They want specific changes in their own, the part of the product that they're buying. So that personalization often, leads to what we call as n equal to 1, or sample size of 1, or in the manufacturing terms, lot size of 1. Additive manufacturing and 3D printing precisely bring that capability of manufacturing a lot size of 1, so that in the industrial production we are saying, especially when there is price performance ratio is good, and that's a possibility. And of course, it brings automated quality inspection. We talked about it in the just-in-time manufacturing, and also for example, when I say unique parts, what happens is I recall a couple of years back I was working on a project with the large engine manufacturer where they were looking at applying 3D printing or additive manufacturing as a concept, not for the regular engine parts which are kind of produced in hundreds of thousands, but they had situations where they were engine parts that were kind of from a few years back, and the original supplier who actually made that part did not even exist now. So when they had to replace some of these parts in engines being used in the field, so they had to look at new source of production. They had to kind of go and identify new suppliers and onboard them, prepare them, and of course, none of the suppliers are going to produce just give you one part, because for their economics to work, they're going to produce a minimum lot size. So in order to kind of meet that challenge, that particular engine manufacturer actually looked at additive manufacturing as an option, and they successfully adopted this to kind of print what I call as rare parts, which are required in the field, and you don't have to go through the traditional manufacturing process. You can use additive manufacturing to design and print, print those parts. Industrial production sometimes. Parts are also improved by bringing new materials. A part could be made of metal. It could be very heavy. Additive manufacturing process actually enables manufacturers to look at different other options. They can use different other material. In this case, a polymer that is as strong as metal or something like that, so that can be used to replace that original material, and hence achieve both cost reduction and also weight reduction, for example. Then in this case, industrial production, I just don't want to repeat, but this is the classic example. We saw the example from the energy industry of the burner successfully being converted into a 3D printed part that is used in the industrial production of this part. So in summary, the broad applications of additive manufacturing that are used today, predominantly a lot in tool development, it's being used, and then and also in rapid prototyping, improving the cycle time there. And in industrial production, there are some examples, but we have to have a business case for that to be used in the industrial production. This will be a complex product where it is multiple parts, or it is be a material, drastic improvement, or a real need for, a unique differentiation across customers and things like that. You also mentioned about one of the killer apps that additive manufacturing brings is the complexity. It allows you to now manufacture complex products. Can you explain a little bit more, or also tell us what kind of problems is the additive manufacturing concept allowing us to solve now? What are the new problems that you're solving?
So as you mentioned, I often describe additive as being a production process that allows you to make really complex parts. And you'll hear it often mentioned that with additive, complexity is free. It's not exactly free, but it's certainly a lot less costly than it is with some of those other manufacturing methods. And what that buys you is the ability to make a part that with more freedom than you would make using other design or production methods. When a person is designing a product out in the world, so let's say we're designing a car and we need to make maybe a bracket for a seatbelt. We have to design the part so that it can eventually be manufactured. And in the past, that meant you had to design that part for machining or for injection molding. And there were certain things that those technologies couldn't do, certain geometry types that those technologies couldn't produce. And additive gives you much more freedom to create all different kinds of geometry types. And that basically also allows you to make parts that do a lot more than parts from these other production methods. So for example, the way cars are made now, you may have an assembly of parts, 5 or 6 different parts that are joined together with bolts or screws or bearings or things like that. And those parts are produced individually because that allows them to have a simple geometry that can be made using those traditional methods. With additive, you can oftentimes take those 5 or 6 parts and combine them together into a single part. And that single part's going to be much more complex than those individual parts were. But again, with additive, complexity is relatively free. So it doesn't cost you much to do that. And it saves you a bunch of time. You don't have to assemble those things together. You don't have to get them from different suppliers. You're manufacturing them all in one piece. So it makes the assembly of the car much easier. So there's all kinds of benefits that come downstream from that. But there's other things too. So complexity allows you to do things like make custom parts for people. So we're seeing this in the medical industry where people are designing things like hip implants that are made specifically for a patient's anatomy. So in the past, you'd have a multitude of different implants, and you'd kind of go through in the middle of surgery and choose the one that you thought might fit best for that patient and use it. And now you're going in before surgery, you're scanning that patient's anatomy, you're using their exact anatomy to design that implant. And that means that implant, again, is much more complex than the original one would have been, but it also fits that patient perfectly and allows the surgery to happen much less invasively, giving that patient a much better outcome overall for the surgery. So we're seeing all kinds of uses here that kind of come from the ability of additive to replicate these complex geometries in a fast and pretty effective way.
So that means, you take a complex product and you basically are eliminating the manufacturing process of each of those individual parts. Then you manufacture this, the complex unit that's put together, and that's very interesting. And your example about the medical example, because it is personalized to the individual, and that's where this becomes very very relevant for in going with additive manufacturing context. Today, we have three leading experts from General Motors who've got decades of experience working on additive manufacturing. First, we have Ali Shabir, who is the engineering group manager for additive manufacturing product applications. And then we have Dominic Lentin, who is the group engineering manager for additive manufacturing applications. And finally, we have Ron Dahl, who is the director of additive manufacturing at General Motors. So welcome to all three of you, and I really thank you for taking time to spend with our learners.
Our pleasure. Thank you.
Yeah. Ali, I will start with you first. I mean, because you are focused on the technology. I mean, so, what is this additive manufacturing? Why is it becoming so popular and being talked about now more recently in manufacturing? And how has been the journey at Michigan and sorry, at General Motors for you guys in terms of using this? Both in the auto ecosystem, you're one of the biggest OEM players at auto manufacturers. And where do you see this technology evolving?
Yeah, absolutely. Thanks, Krishnan. So additive manufacturing is both simultaneously new and old in the auto industry. Right? So General Motors has been using additive manufacturing, 3D printing, rapid prototyping, whatever it's been called, for well over 30 years now. In fact, we had one of the first machines ever commercially available right here in Warren, Michigan at our technical center campus. And we've historically used it a lot for prototyping. And being able to get some early proof of concept, try out components and parts as we develop our vehicles, as designs of parts and systems evolve. And then recently, we've heavily invested into expanding the usage of additive manufacturing, 3D printing, throughout our entire vehicle portfolio and throughout our manufacturing operations. So what that means is, how can we use this technology to produce parts throughout the product development cycle for our vehicle programs, for any other products we develop, and then also in our manufacturing operations, in our tools and our capital investments that we make to allow us to produce parts, produce vehicles with higher quality, reliability, speed, and better cost, whatever that may be. So that's really the perspective of how it's being applied and what it is truly, right? To step back a little bit, additive manufacturing is a field of manufacturing processes. It's not just one single type of 3D printing technology. And the one thing they have all in common is you are directly producing parts layer by layer from digital data. So there's no tool involved that helps form your part into a certain shape. And you're not machining away material, for example, tracking it. You're truly adding up the shape of the geometry of the part in consecutive layers by depositing material or by melting material, whatever it may be. So this technology affords a lot of flexibility in how you produce components and the speed with which you can produce them, the cost with which you can produce them, and the design features and the performance that can be enabled. There's just certain things that you can now create in terms of the design or geometry that you couldn't really do with traditional design for manufacturing limitations you may have in those manufacturing processes. I'm talking injection molding or stamping or casting. So the last thing I would like to say is that additive manufacturing is another tool in the toolbox. It's just one of many manufacturing technologies, many manufacturing processes that are used to produce components and to produce whatever products that you're working on. It's not going to solve all manufacturing challenges. It has very specific use cases and applications where it shines, and that's truly where it should be used, rather than trying to apply it in broad strokes and replace all your other manufacturing processes. Just like any product is made with dozens of processes, additive is just another tool in the toolbox.
Great, thanks, Ali. Ali, you mentioned that you actually now moved beyond prototyping, applications of additive manufacturing to more the end-to-end different aspects of the product, even in manufacturing. So, Dominic, I was wondering, can you give us some examples of where you are now, using the technology, beyond prototyping?
Yeah, I think like what Ali said, additive manufacturing can be used in many different aspects. Still doing a lot of prototyping today. Still looking at some opportunities and some wins of putting it into our commercial vehicles. But ultimately, it's changing the way that we develop new products and accelerate our development time. Some examples are cutting out tooling costs from our pre-production vehicle builds, cutting a lot of capital out of that by direct printing parts in pre-production vehicles. And another very big space is manufacturing tooling, right? We have a lot less requirements from a validation standpoint with bringing a new technology into manufacturing tooling. And we can very simply implement lighter weight, lower cost, and quicker to manufacture components within our assembly tooling space.
Great, thanks. So that is useful. So basically, from prototyping, you're now more into tooling. Are there any examples that you're also kind of using this technology in serial production?
In terms of serial production usage, General Motors is actively pursuing opportunities to use additive manufacturing when it comes to low volume production of components. So there's certain vehicle platforms, certain vehicle programs that have volumes that are in tune with current capabilities of additive manufacturing that make economic sense and performance sense. Beyond that, looking at opportunities in other specialty use cases, such as service components, such as accessories, such as motorsports and racing programs. These are all opportunities where additive can shine. It can add value beyond just cost and timing benefits, but actually performance of the parts as well. As the capability of additive grows, right, as we get better, faster, cheaper with those components, we can certainly look to see expanded usage of additive in serial production programs at higher volumes in different vehicle programs and platforms.
Now that we have understood what additive manufacturing technology is, and also we have discussed some of the criteria, let's look at some of the industry applications. Basically, understand which are the industries where they are rapidly adopting this technology, and then we'll see why. So in this chart, we have 4 industries listed: aerospace, automotive, healthcare, and consumer products. I think additive manufacturing is being adopted in these industries. First, let's start with aerospace industry. And as we can understand, each industry has got its own constraints and requirements. So in the aerospace case, they certainly are going to be low volume as needed in additive manufacturing, and also they will pay a lot of premium for anything that we can do to improve the design of parts, and change the geometric shapes to kind of reduce the weight or material consumption. So that's actually what drives applications in aerospace, and the focus there is on strength of the material, performance of the material, and then weight of the material. Automotive industry is also actually adopting additive manufacturing, kind of quite rapidly in the last few years. But certainly in automotive industry, it's not widespread, obviously, because automotive manufacturing, unlike planes, is not in hundreds of thousands, but actually it's actually in thousands and millions, right, in terms of number of cars that have been produced. And so additive manufacturing is applied in specific aspects of specific areas in automotive, not widespread. So, for example, we talked earlier rapid prototyping, and also in new product development. New product development, when they have to create prototype and then you have to test, and then so the introduction of additive manufacturing is certainly helping auto companies shrink the total time it takes for them to come with new part or a new product as well. And there are several benefits for the consumers as well in terms of of course, cost and weight reduction, just like we saw in the aerospace industry. But we also see the capability for auto industries to even personalize products, and that can come from 3D printing. And both in aerospace and automotive, of course, this is bringing reducing significant amount of wastage. In fact, saving more wastage in automotive industry because of the volume of production. So those are some of the applications in the automotive industry. Another interesting, industry that actually is adopting, additive manufacturing or 3D printing is healthcare industry, because healthcare industry, basically is uniquely positioned, in terms of, the applications here or human organs, right? Human organs, by definition, are going to be unique to an individual. For example, my fingers, my hands are not going to look, similar to anybody else, my friends or even my family members, right? So that's the unique feature that we have. And if a human organ has to be kind of printed, then naturally it can lend itself to additive manufacturing, right? Where you can take sometimes the capability of 3D sensors, like we can scanners, where you can actually take a particular existing part, you can scan that part and get the full information about the 3D image of that that shape, so that can be done with organs as well, and then you can reverse engineer that and then create that particular organ that will perfectly fit that particular individual. So this personalization and lot size of 1 or n equal to 1, we've been talking about the market pressure coming to manufacturing, and that's true in this industry of taking care of organs replacement in healthcare industry. And so that's a classic example of additive manufacturing is used. And the last, consumer products. In fact, we see that more recently 3D printing and additive manufacturing as a concept is kind of rapidly coming into the consumer products as well, because it now, additive manufacturing, not just the printing aspect of it, but the ability to explore the design space to find to new design structures, new design solutions, which basically allows the consumer product industry to reimagine products and reimagine how the products are used, and those kinds of applications actually driving the adoption of additive manufacturing in this industry. And of course, added to that, rapid product development and customization of product and unique uses of these products. And another industry actually not listed here, which I want to kind of emphasize, is also in fact championing in the adoption of additive manufacturing, is the defense industry. In fact, defense is one of the pioneers in terms of adopting this technology, because again, as you can imagine, defense industry, whether you're actually looking at parts for a tank or any of the defense products, right? They are not going to be again, they're going to be not very high volume, not all of them, and then also they're going to be paying the premium premium price for any strength and performance of the product that is manufactured. So the criteria we talked about, price premium for performance, right? Because in the defense industry, of course, as you know, I mean, if there's any quality problem or things don't work or things can be improved, they certainly will improve, because what you're playing with is the risks and the cost of human life. So that's why that industry is kind of is on the front of exploring and innovating using additive manufacturing and adopting this technology. So let's look at some of the examples in these industries. Now, first starting with the aerospace industry. We saw this part used in airplane seats to reduce the weight and strength of and reduce the cost as well. In fact, just to give you an idea of the market size and how fast this is expected to grow, a recent U.S. car report states that General Electric Aviation replaced 900 parts with 16. Right, so basically they've replaced 900 parts with 16, almost like 1:50, right there in terms of the ratio there, because what's going on there is they're able to kind of take some of these parts, they eliminate the part, or they'll combine the part into one part, as we saw in some examples earlier. So they're using this additive manufacturing to reduce the number of parts, and that's a big benefit in the helicopter engine build. So that's one example of giving you an idea of the scale of the change that additive manufacturing is bringing. And then there is this global industry analysis. They came out of the report which states that in the aerospace industry, our additive manufacturing and 3D printing is expected to reach $4 billion in market size by 2027, and that is projected growth of almost 24.4% compounded for the next 6 to 7 years. So that gives you an idea of the market, the adoption of this technology in this industry, and also the impact of this technology and the market size as well. Now, on the automotive industry, as I said, not used in serial production of millions of vehicles there, but there are unique applications like motorsport, right? Racing cars, racing motorcycles, and that's a market in automotive industry where it is going to be low volume. We're not going to see millions of racing cars, right? So the low volume again meets the criteria, and in fact, this is a partnership with between Siemens and Hackrod, where they are actually kind of using additive manufacturing for looking at redesigning the entire vehicle frame. And they are looking at producing the entire frame with additive manufacturing. This is a unique example because usually additive manufacturing is constrained by size, as I mentioned earlier. But there are experiments where they are looking at, looking at the capability being applied to entire. If they're looking at the entire frame as one particular unit, and so hence they can redesign it to, certainly reduce the weight of the material or the entire frame, and that will help in the aerodynamics of the car, or kind of the speed of the car, which are important dimensions in this industry. So basically, they are able to kind of pay the premium for the performance of the parts and overall performance criteria, and that's why this is a classic example of how it's being used. Now, in the healthcare industry, as I talked about, this is again worked for Siemens is one of their partners of human hip replacement, right? I mean, if you kind of you have to scan, it is personalized by n equal to 1, and then you have to kind of have a perfect fit there, and so that's a classic example that it lends, and there's people are going to pay premium for that personalized organ that is printed or a part that is printed for that individual. More interestingly, in this industry, and specifically in this application, I think there are some future trends which are very promising, because traditionally, when you're actually kind of putting a metal to replace a joint, or putting a hip joint, and you're replacing it with a metal or ceramic or whatever the material that is used, is often seen as a foreign material by the body. And in fact, in these cases, patients actually take medications, right? I mean, prescription medication, lifelong for their body to accept that foreign material. But there are promises in terms of the research being done in additive manufacturing, where they are thinking that you can take the human cells, human genes, to kind of create the material, and then use and create and print the part, or create the part using additive manufacturing with that material, so that it is naturally accepted by the body. And you can imagine the kind of benefit that brings to the healthcare industry and to the patients, that they don't have to take this medication drugs for the body to kind of accept this foreign element that is attached. So this is also a classic example of low volume demand, and so that's why it lends itself into nice application for 3D printing. Then coming to the consumer product goods, as we talked about, this is an example of Siemens working with one of the customers in the consumer product industry to create the soles for the shoes, right? And here they have actually kind of used additive manufacturing to kind of create the design in a way that it brings comfort, it brings the weight absorption capability, and it's an optimized design. Kind of they have used lattice optimization structure, techniques to kind of and experiment with multiple materials, different materials, to kind of bring this lightweight product, a lightweight part that kind of certainly improve the comfort level and the performance of shoes. And of course, here it is used in the rapid prototyping, so that they can kind of look at different options. And obviously, this can also be taken to further, where again, shoes are a classic example where we have our foot, they don't look same. All of us have different needs in terms of perfect fit, right? And so if you look at you scan the foot of a person, of a customer, and then you have a 3D image. And you can convert that into kind of real need for the shape of the shoe, exact shape of the shoe, and that could be 3D printed. So these are some of the examples in the consumer products industry where you can use this technology, and the 3 industries or the 4 industries we talked about. And in defense industries, certainly there is classic examples of where they have unique parts that they don't manufacture in large scale, but they just want real special strength or performance of the material, and that's why I use additive manufacturing. We have so far described additive manufacturing as a process where you create a part or build a shape, by printing layer by layer of different materials. Well, behind that process, I just want our learners to understand that there are so many technology choices. We know that the purpose of this course is not to understand those technologies, and this is not a technical course. However, I believe that it is important for our learners to be appreciative of the variety of technologies that are available, and all these technology choices, they come with pros and cons in terms of the capabilities and also the cost. So just to kind of go through some of the process and the specific techniques used to how the 3D printing of the actual real printing, how does it happen in an additive manufacturing process. I think we've just captured some broader information here. This is not exhaustive. I just want to kind of want our learners to know that this is just some broad categories and some specific techniques within these categories. So when you think about a layer by layer printing of a solid part, right? Certainly, of course, you're using some material, and then some way you have to convert that material to be in a flexible form to create those layers, right? And the broader techniques that are used, or first we call it melting, where you use some energy source to melt that material into a liquid, semi-liquid or near liquid form, so that it can be then used to create those layers. The second is called sintering. It's kind of again a technical term, but when you say sintering, when you heat any material almost near to the melting point, not up to the melting point, the sintering is called heating up to the very near to the melting point, and that's what is done in this process, where the material that is picked, whether it's metal or polymer, it's basically the powder, or it is actually heated to that near to the melting point, and then it is used to kind of bind together to form that particular shape. The last one, stereolithography, is more like a photochemical process where this technique actually uses UV ultraviolet laser as a kind of energy source to kind of create these photochemical reactions to kind of heat that particular material and make it bind. So this is a classic example of a digital design of a part that you want to 3D print or additively manufacture. That you have this this CAD software, the design file, contains all the information about the strength and the shape of each of those particular surfaces of the part. And this information is all coded in the file, and it will be read by the software that will be used by the 3D printers. And when you want to print that particular part, you can have, in some cases, you can have any of those technologies, and in some cases, depending upon the part or the need, you may be able to use only one of those. But this is a kind of a more a business choice as well, and also as a technical feasibility choice. Just to give you a flavor and example, let's look at a couple of these, in the diagrammatic form, how they work. In the powder bed fusion, you see there is a energy source basically, brings the heat to kind of to melt that particular material, and then that fusion of the material happens, to create the shape that is required. So you have the powdered material that is actually taken, and then this energy source heats that material to kind of convert it into liquid form so that it can be fused to that shape. The other popular technique called the material extrusion that we saw in the last category, right, where you have heated material is actually is the extrusion of that material through a nozzle, so that you can then almost print it like quite similar to what you see in your inkjet printer that you use at home for or office for printing paper, right? And that's exactly what's used with this material that is used to create 3D printing object. Often the question is also raised that, additive manufacturing comes at a cost, right? So can you give us
a broad overview of what are the different kinds of additive manufacturing technologies, right? I mean, we sometimes use resins, we use metals, right? Metal powder, I guess. So what are these broad categories, and how do they compare in terms of their both cost and also the degree of difficulty in implementation?
So I'm going to break this down two different ways. I'm going to break it down by material, and then I'll break it down by process. So materials, for the most part, tend to run between polymers on one hand and metals on the other. Those are the two main ones. And you hear about some others like ceramics and composites and things. But in general, you're mostly talking about plastics and metals. So if we talk about the plastic side, that is everything from your desktop printer that your child maybe uses in school. They're printing out little rabbits or widgets or whatever, for fun. And that's honestly the way I learned about 3D printing way back in the day. But those polymer printers now go all the way up to full production scale printers that are churning out hundreds of parts for real world applications 24/7 in a factory, just like you would expect, right? So they run the gamut. And the ones that are small and desktop, printers are fairly inexpensive. Less than $300 these days can get you a pretty good one. The plastics that they use are things like ABS, which is a very common plastic used all over industry. So it doesn't cost very much. The materials are readily available. All the way up to those high-end printers, which are the size of a refrigerator or more. They're costing, tens of thousands of dollars, and they're almost always using some sort of powdered plastic material and fusing that together. And the reason is because the powder allows them to get much more resolution than the injection or the little, filaments that you normally use for a home printer. So plastic kind of runs the gamut from really small desktop stuff all the way up to professional stuff. Metal is a much different process because powdered metals can be hazardous, so you're not going to use those in your home. There are a few methods for metal that will eject a material, like a hot glue gun, like the plastics do, but those are pretty few and far between. It's basically akin to welding, if you think of that. And all of those metal processes are pretty expensive processes. The materials alone themselves, the powdered metals that you're going to use for that, are pretty expensive from a material standpoint. And the processes use a lot of energy using things like lasers usually to fuse the material together. So those are definitely more expensive, higher end, real production technologies. The other thing we talk about is the processes used. So on those desktop printers, you're taking a plastic filament, you're melting it, and you're pushing it through a nozzle, ejecting it, in a certain pattern. And that's a technique that's been around for a while, mostly exclusively, like I said, used on plastics. When you get to the higher end stuff, the metals and things like that, you have a lot of lasers being used, electron beams being used, because you have a much higher melt point for those different materials. And if you get even beyond that, what you see is people are starting to mount print heads on the end of robot arms. So, most of the print technologies we'll talk about today are planar. You're laying those sheets of paper on top of one another. But these 3D machines are more like paper mache, right? You're taking some 3D form and you're printing in 3 dimensions around some 3D form. And that's a much more complex, much more niche kind of product, but it's out there and people are using it today to do things like aircraft parts. So it runs the gamut. You can do a lot with plastics, but you get up towards the production stuff and it's usually metal and it's very complex and expensive.
Great, thanks, John. So you did mention that we build parts, right? But you don't always build parts the way we build parts in the traditional manufacturing, right? So tell us more about that.
Yeah. So we at Fast Radius we use a variety of manufacturing processes to create our parts for our customers. Additive or 3D printing is one area where we have built a real strength and we believe a deep differentiation on the market. And so we use three main platforms. So we focused mainly on polymers to start, and I can maybe talk about that choice in a little bit as well. But we focus mainly on polymers and three main platforms right now in terms of carbon digital light synthesis, HP multi-jet fusion, and then Stratasys fused deposition modeling. So those are three additive manufacturing technologies, all slightly different in how they create the parts, but all essentially additive based rather than subtractive based. We also do more traditional methods. We have a machining facility as well as injection molding and other facility or other technologies that we service through a partner network. But additive is really kind of our beachhead tech kind of suite that we've really made inroads into the market with.
John, thanks for that overview. Very, very useful. I mean, and we can see the excitement in terms of in the intersection of digital technologies and manufacturing.
In order for us to learn how companies make decisions on when and how to use additive manufacturing, even though the technology is very impressive, but they have to look at the economics and the broader implications of implementing additive manufacturing. So, in order to understand this, let's now look at the economics here. Let's start with the traditional manufacturing, right? We all understand traditional manufacturing. If you want to kind of say manufacture, let me go to my box again. If you want to manufacture, thousands or millions of these boxes, then whatever the traditional manufacturing, technique we're using, there's going to be a huge setup cost, right? What you see in this picture is, you have volume on the x-axis and your total cost of manufacturing these boxes on the y-axis. So you would have a huge setup cost to kind of start making these boxes, and whatever the traditional manufacturing technique you've used, whether it is your die casting, injection molding, or how you're going to use this, make this box, there's going to be a big setup cost. Then once you incur that setup cost, then you can, as you increase the volume of the production, right, and you make more and more boxes, that total cost is not going to be increasing that steeply. In other words, what we call the economics of scale, where you produce more parts, then your total cost doesn't increase that fast. And what does it do? It actually brings down the average cost, kind of for producing, right? The marginal cost and average cost actually coming down. So if you look at the average cost per unit of this box that I need to make, the more I make, my average cost of making one box actually comes down, right? That's because there is the economies of scale. That's how the traditional manufacturing works, and we all understand. We have read this, we have studied this in economics, and you've studied this in operations, all the place. In additive manufacturing, that's not the case, because in additive manufacturing, there is not one huge setup cost that you're actually kind of using for manufacturing, thousands and millions of parts, right? Which is kind of so that fixed setup cost is distributed across all these thousands of parts, and that's bringing the average cost down. But in additive manufacturing, as it is shown in blue in this chart, you actually print every box separately. You remember that when we explained additive manufacturing, you're going to use whatever material you picked, and each of these boxes would be printed layer by layer, right, one at a time. So that's why you are not going to see that steep reduction in cost, that economies of scale that you see in traditional manufacturing, you are not going to see in additive manufacturing. And that's the reason where I mentioned additive manufacturing may not be suitable for when you're kind of, manufacturing millions of parts. Traditional manufacturing still wins from a cost standpoint. However, if you look, there are also other benefits, economic benefits of additive manufacturing, that we need to understand. In this chart, there is a very simple, XY chart here. On the x-axis, somehow imagine it is efficiency, right? It is kind of, you go from left to right on the x-axis, it is increasing efficiency, and the y-axis is about flexibility, right? Traditionally, in traditional manufacturing, the more flexible you want to get, the less efficient it will be. For example, flexible in the sense, one way of defining flexibility is, let's go back to the demands that is placed on manufacturing units. Say, for example, the lot size of 1. Personalized experience for customers, right? If in an auto manufacturing context, if all of us want our cars to look unique, have different features, then what is going on is the flexibility is going up, right? They need to have the variety and flexibility to make one car for each one of us. But when you increase the flexibility, the efficiency will come down, right? So efficiency will actually be reduced. That's why you see the curve that as the flexibility increases, you have the efficiency is going down. So that's a traditional manufacturing. In additive manufacturing, what happens is it actually kind of pushes that curve because of the capabilities that we talked about that is coming with additive manufacturing. First, number one, additive manufacturing actually allows you to kind of explore new design options, right? It brings the capability where you can actually kind of new customization, you can actually new shapes you can do, and that may not be possible in the traditional manufacturing set, right? And additive manufacturing can actually do that with those changed designs and that variety, and also use the same additive because it's going to be printed one at a time. It can still give a little bit more efficiency than the traditional manufacturing. So it actually allows you to kind of look at new design options because of the algorithms and simulations and modeling that you could do with the software. The second, it actually, the efficiency increases through automation and part consolidation, right? We saw example in the burner example where we combined 13 parts into one part, right? Then that is bringing new efficiency now. Instead of kind of producing 13 parts and combining, you're just producing one part. That actually increases the efficiency further, and for the same kind of flexibility. And of course, the last we saw the example of rapid prototyping, which the 3D printing technology and additive manufacturing allows the manufacturer to experiment various different variants and also speed up the process of prototyping and also bring in new design of the parts into manufacturing. So that process actually again shifts this curve between flexibility and efficiency. In other words, in summary, what I want to say in this slide is that additive manufacturing actually brings a higher level of flexibility and without losing as much efficiency as you would lose in a traditional manufacturing context. So if you understood these, cost trade-off and then the kind of the benefit that are coming with additive manufacturing, so certainly additive manufacturing brings a lot of these benefits, but however, it is not directly applicable to all manufacturing situations. So there are criteria, right? There are kind of that you need to apply to select when would you use and choose to use additive manufacturing. And these criteria are, number one, low volume. When you have low volume, a market where there is low volume of parts, right, then what happens is that you are losing the benefits of economies of scale that comes with traditional manufacturing, right? That's why additive manufacturing is a viable option. Examples are motorsports, aerospace industry. You don't make millions of planes. You may make hundreds of planes, or you may make thousands of planes, but you don't make millions, as in a car part. Or the second example is tools, right? In a manufacturing context, you may make millions of these boxes, but you don't make millions of tools that make these boxes. So tools is a classic example. The second criteria is the price premium for performance. You need to see that the customer is willing to pay a premium price for the performance of the product. So as in the case of aerospace, when you reduce the weight of that part by 1 kg, right, they are benefiting by thousands of dollars. So they would be willing to pay the price premium, and that is suitable. That scenario is suitable for additive manufacturing because you can improve the performance of the product even though the cost may actually go up. Second, complex parts. And I don't want to kind of repeat that with the burner example where you combine 13 parts into one parts and the consolidation of parts and bring a new design. And the last one is the personalization, right? I mean, the N equal to 1, lot size of 1 demand coming into manufacturing. And for that, manufacturers can respond to that only through digitization. So additive manufacturing allows them to digitize the design of the part and then also make it flexible that they can actually kind of do the minor changes that are required, that may be required for every customer, right? In this case, additive manufacturing by definition, by design, it's going to be lot size of 1, and that gives the option for manufacturers to be flexible and make the changes. And classic example in this case, I would say in healthcare I will talk about the applications in healthcare where you need personalization and additive manufacturing. That's why it's used in manufacturing of human organs in healthcare industry.
You mentioned that as you kind of provide cloud-based services in manufacturing, right? You do both the traditional injection molding, those kind of methods of building parts, and predominantly it's the beachhead, of its additive manufacturing. So how do you suppose a client comes to you? How do you decide which particular case, which particular part is ready, should be done in 3D printing, and which should be done in a traditional manufacturing way?
Mm-hmm. Yeah, absolutely. So there's I would say a two-step screen, and then we talk about 4 archetypes. That assuming that the two-step screen, it's kind of a go no go. Then we help our customers think about 4 archetypes that drive business value when using additive or 3D printing. So the first screen is very go no go, and that's materials. Additive has made tremendous strides over the past 4 or 5 years in regards to materials performance. And so there is a much wider suite now available of materials. And I would say most injection molded kind of polymers have a good analog with an additive or 3D printed material. And so that would be the first one is, does the material suite out there, can your parts or products requirements be met by a material suite? So assuming that is the case, then the second is economics. And so we will, work with our customers to build out, an economic understanding of how do we think about, the business case. And typically, that's where these archetypes that we talk about come into play. So the first one is accelerated new product development. So can there be additional value by moving through the product development process more quickly? So rather than doing a 3D printed prototype, maybe for fit and finish, kind of fit and form, and then doing a low volume injection molding run, and then tooling up for a larger run, can, by using additive, where you're essentially prototyping on the production platform, and you can get design iterations much, much faster. So, a great example of this is we worked with Bastion Solutions, which is a Toyota company, but they do material handling. And so we worked with them on a robotic arm that would do pick and place in a warehouse. And we tested over 100 prototypes. We helped them create over 100 prototypes in 20 months. So this was rather than, that 20 months was probably about how long they had to make the product anyways, but they would have tested maybe 10 prototypes in that amount of time. And so we helped them to ultimately create a better product. So that's the first one, is accelerated new product development. The second is spare parts and supply chain. And so this is, when a lot of people think about 3D printing, especially, every couple of years, there's this big hype cycle over 3D printing. There was one in 2014. There was one last year, actually, with COVID, medical equipment and replacement supplies. So this is qualifying additive as a secondary process to supply spare parts. So an example for this, we work with Airbus Satair, which is their aircraft maintenance business, where we print parts on demand when they need to order tooling. So it's essentially they have an aircraft on ground. They need some tooling to help repair, make a repair, do maintenance. And we cut their lead time from 2 months to 2 days.
2 months to 2 days.
Yeah, it's pretty fun. And we did the little stopwatch in a box, and we shipped it to them. It was pretty fun. So we had that set up, and additionally, this cuts their need for inventory as well.
So this is this is spare parts example, is that right?
Pardon? Yes. Yeah.
So when they started the business case, did you expect 2 months to 2 days as a?
No, we like to be aggressive and bold, but that was a lot faster. Though I will say, that is not an unsurprising outcome, just because the turnaround time, especially if you're producing a part, if it's designed for additive and takes advantage of what you can do with additive, you can produce a part that needs minimal post-processing. So you can essentially, assuming there's capacity, and we're talking, a manufacturing process time of, let's call it 5 to 12 hours. You can get it on the printer and off and shipped.
What does this part exactly do?
There's actually a variety of parts. I don't know the latest count of parts that we have, and we call it the virtual warehouse. But these are jigs and fixtures.
Okay.
So when there's an aircraft on ground and they're doing maintenance, there's a lot of safety jigs and fixtures, that they put into place.
Great.
Yeah. So that's the second. The third is mass customization, or low volume, it also calls low volume variants. Additive is a very, it's a kind of a fundamentally, by its nature, flexible manufacturing platform. And so how can additive enable more cost-effective low volume production, or low volume production that wouldn't even be made possible before? So, and low volume can also vary by industry. So a great case example of this is for Aptiv, which is an automotive supplier. We supply electrical connectors for the heavy duty. It's the Ford F-250. So this is for customers that order the heavy duty pickup, but forego the tow package. And so, as you can imagine, there aren't a lot of customers that get a heavy duty pickup and don't get the tow package. And so we produce essentially the delete cap. So it is a plastic cap that goes on to some of the electronics at the back of the pickup to essentially delete or block off the tow package. And so for them, that's low volume for them is in the tens of thousands. And so we produce tens of thousands of those, a year. And they go on the pickup, on the exterior of the pickup. They've met all of Ford's and Aptiv's material requirements for performance on the exterior of a vehicle, and then ended up with a great business case for them.
Actually, I would now like to understand the economics of additive manufacturing. I know you did mention, the examples in auto and aircraft. That is very interesting. So, is it true that it's kind of you need to go to additive manufacturing only if the product that you're trying to make is fairly complex? Okay, and as compared to, say, if I'm making a simple widget and I have demand that is scaling up in thousands and tens of thousands, then is it okay to say that additive manufacturing technology economics is not caught up to the to the level that we can use it in this mass scale manufacturing?
There's definitely a threshold for that, right? So there's a kind of an inflection point where, if you have a low lot size in the maybe tens of thousands, you can probably get away with additive and be okay. When you're talking, let's say a normal automobile manufacturer in the US turns out, I think, something like 5.5 million cars a year. When you're doing things of that size, or iPhones, they make 5 million every time a new iPhone comes out, that sort of thing. Those are scales that additive is not yet really suited to scaling up for. 10,000 parts, yeah, you can crank those out pretty quickly, but you get into the millions and it's much more difficult. Now, that being said, there's a lot of people working on that problem and a lot of creative, just in the past maybe 2-3 years, lots of the hardware companies have started working on how to generate more output from the technologies we have. And also some new technologies are coming online. So I've seen some very interesting, polymer technologies where they're getting to the point where they can probably start producing polymer parts to the scales that, are interesting for an automotive manufacturer. So I don't think it's going to take terribly long to get there. But again, it depends on the material and it depends on the use case and things like that. But there's definitely sort of an inflection point where you kind of do this calculus about how many of these am I going to need? Will it make more sense to do something like an injection molding where I can pump out, millions of these parts really quickly? Or do I need, the advantages of additive for this particular situation? And that overcomes that, the economics of making lower volumes. So yeah, there's definitely some work to be done there. But it's to be honest, I've been amazed how fast things have changed in just the past maybe 5 years on that. So I expect that trend to continue. I don't know if we're at a Moore's law situation, where things are going up exponentially, but they're certainly increasing quite rapidly. So that's good news for the future.
Just to follow up, based on what we see, hear about additive manufacturing, one of the areas where it seems to be a challenge is the speed at which it can print. I mean, a particular part is being printed when you see a 3D printing, mechanism in action, then it just takes minutes or hours sometimes to. So, do you think is that a constraint when we compare additive manufacturing with the traditional manufacturing?
The way we encourage our customers to think about the calculus there is that the production of a part, the actual producing of that part, is only one part of the full cycle of getting a part and delivering it to the end use situation. So there are things like logistics and storage and transportation and all sorts of things you have to worry about as part of that entire process. So yes, additive might take, 3 days to print a part, whereas you might be able to machine it in a couple hours. But additive also allows you to do things like distributed manufacturing fairly easily, where, the same part can be made anywhere in the world. So, maybe you make the part closer to where it needs to be in the end and for your factory, so that you cut out the logistics that you have, the shipping, the storage, the whatever on the front end, and allow that time instead to be used printing the part. So there are certain ways you can kind of like massage the math on things like that, but it's very situation dependent, right? In the end, what we're going to have to do is scale up the technologies themselves. And like I said, companies are starting to do that. So for example, in the early days, if you had a system that used a laser to fuse a powder material, it would almost always have a single laser. We're seeing systems now that have, I think, 8 lasers, 12 lasers, right? And they're whipping out parts, in multiples of time from what they used to do. So the speed is definitely coming up as the technology matures and the companies that make the machines learn more about, the process, the materials, and all of those things, and what they can and can't do with the physics. So yeah, I think there's some really creative people working on those problems. And again, I think it's really only a matter of time.
Let us now talk about the additive manufacturing ecosystem. We need to recognize that this is an emerging technology. Of course, it has been kind of there for a couple of decades, but now in the last few years, it is now rapidly being adopted by the manufacturers in various applications we talked about. And the promise of this technology and this whole broader manufacturing process is validated by, and the potential is validated by, significant investments that we have seen from angel investors and, venture capitalists and private equity firms. Basically, the flow of capital into this technology is quite impressive. Of course, that involves investments by existing and large manufacturers as well, but it's a lot of startup players. In fact, you would find hundreds of companies now in this ecosystem of additive manufacturing. In order to understand this ecosystem, let's kind of, I think one way to do that would be, as we discussed earlier, the path of what exactly happens in an additive manufacturing process. If you follow that, then we can look at different kinds of players, and then we can then look at the structure of the ecosystem. So as we discussed earlier, additive manufacturing process actually starts with the digital design of the part or the product that's going to be 3D printed, right? So that the CAD model, and then there are sophisticated software platforms that allows companies to, the digital modeling of the design, and also use optimization techniques, sophisticated algorithms, analytics to optimize the design for various design parameters. And there are a lot of companies that actually kind of focus on that and provide this platform. Some are listed here, but not all. That gives you, the role played by those companies. Then the design, once it is finalized, it is actually then converted into printable files, which is actually a combination of the design information and also a lot of information about the printing, what exactly is required in printing in terms of the strength of the part in different places and all this stuff. There are companies that actually kind of specialize and kind of play in that kind of a service role. Then you transfer to additive manufacturing machines, or the 3D printers as we call it. And there are printers, there are companies that actually manufacture these printers. They have different standards that has to be met. And there are companies that actually, which make these files ready for to be 3D printed. There are some services provided like that. Of course, machine setup is setting up the 3D printing. And then finally, the building. Building is where you actually print that 3D part. You print that part, right? That's where there are big 3D printing companies. Only a few of them are listed here. And some of these 3D printing companies have attracted, great, attention in the media, and also in terms of investment flowing into these technologies and these companies. And of course, after it is printed, there is part removal, and then there is post-processing of the part. So these are the steps that are involved in what we do, the end-to-end process of additive manufacturing. And if you kind of go and look at the ecosystem, and I only captured, some of the major players. There are also other players here, which can be added to this ecosystem. I mean, one way to understand this, let's start from the top of this chart. Of course, one key piece of this ecosystem is the companies that have invested. They actually do the additive printer. They manufacture the printers, right? I mean, and that is a very important partner here. We're actually kind of, because a selection of printer is very, very important in terms of their capability, the materials that they use, and things like that. And then there is additive material suppliers. I mean, there is so many different kinds of materials could be used in additive manufacturing. You could actually be printing, 3D printing parts with plastics, ceramics, with polymer, with metal. I mean, you name it. So there are so many of them, so many different materials, and materials also being, discovered, in the research and development institutions, where they're finding out, they're actually testing and discovering new material, combination of materials to kind of improve the performance of the part. So there is that many set of suppliers ecosystem of who bring the material, create material for the additive manufacturing process. Then the third piece I have there is the additive design software providers, which actually we talked about earlier. Like there are platforms that actually provide the design platform to kind of for you to model the design, simulate the design, look at different experimentations, design of experiments, say various options, basically explore the entire design space. These algorithms and these software platforms are now very rich, and in fact, they now deploy intelligent algorithms using machine learning, artificial intelligence, to kind of go and explore the design in a space to find out what are the new designs that are possible for a particular part. So kind of there are companies that actually have invested like Siemens, who actually provide platforms to kind of look at these design options. Then of course the enterprise software systems providers like your SAP, like which is kind of the ERP, and there is a PLM. Vendors like PLM is product lifecycle management software, ERP is enterprise resource planning. Vendors who provide these software, like there's SAP or Windchill, you name it. These are the companies that actually provide this software. Why are they important in this because in this partnership in this ecosystem? Because you may actually adopt additive manufacturing and then you 3D print a part, but that part still has to be integrated back into the software system that actually runs the manufacturing business. That's why that integration is important, to capture the design information of the parts and then connect it with the operation process of the business, right? And then the next part is the integration and consulting organization. Now, as you can see, there are so many moving parts. This ecosystem has got multiple partners, and so there is certainly a value addition that comes where there are consulting organizations that are stepping in, there are integration organization who actually kind of bring the solutions together or help manufacturers understand this space and then connect, in identifying the right partners to put the solutions together. Right? You can see the additive manufacturing service providers. They are an important partner in this ecosystem in the sense, I gave you an example earlier in the course about consumer 3D printing, where I talked about cloud-based companies where you can actually have it, if you want a mouse or a bottle printed, then you can actually, take a picture, they scan them, I can send it to them, they can actually use that digital information and they can actually process the design and they will allow you to, on that cloud-based software, allow you to, pick the material that you want the product to be printed, and then they will print it, and then for that appropriate price, they will code the price and then you pick the price and the material, and they will actually print it and send it to you. That's what I call additive manufacturing service. They actually provide this as a service. And in fact, even now, I know there are some experiments with UPS looking at this additive manufacturing as a service. As you can imagine, this technology is not only disrupting the manufacturing industry, it is also challenging the logistics industry. If additive manufacturing really becomes, kind of a feasible thing in manufacturing, you can imagine logistics providers like UPS, they don't have to take all these parts in the trucks from place A to place B. If they can get the digital file, they can actually print it at the destination, right? So that's why UPS is basically experimenting with additive manufacturing as a service business. The next is the established OEMs in major industries. And they are an important partner here because large OEMs, like the examples that we have experts, and if you have examples from General Motors or Ford Motor Company or General Electric, these are all established OEMs, billions of deep pockets, and they have, they have a very important role to play in terms of how they are embracing this technology, investing in this technology, and they are part of this ecosystem. And not just established companies, there are also a lot of startup companies as well, right? Which has attracted, as I said, capital market is pouring a lot of money into this technology, and there is an ecosystem of established companies and startup organizations which actually connects, into this bigger ecosystem. And then the last part is the role of academic institutions and R&D organizations. In fact, some of the OEMs themselves have both Center of Excellence, also they have R&D organizations. In addition, there are universities like the University of Michigan, which actually kind of does fundamental research in material science to understand, discover new material. In fact, what I would say is the future trends is to kind of think about the concept of smart materials where, sensors could be embedded into the material so that the material actually would behave depending upon situations. And that information could be input into the design stage of additive manufacturing so that the product can be further personalized for its use. So that gives you overall understanding of what are the different kinds of players who come in together. In fact, each of these sets is itself a mini ecosystem by itself, right? That's why, these kind of overlapping circles we have. And all these things have to be tied together. In fact, this is an emerging technology concept, and it is important to kind of, build this ecosystem, invest, and then kind of build confidence in that for this technology to be kind of widely adopted. It is now in the initial stages, as we discussed in the course. It is used in some stages of manufacturing, but its adoption is kind of quite impressive, and the projected the market for this technology is also phenomenal, as we shared in some of the industry reports.
Great. Thanks, Ali. Ali, you mentioned, that you actually now moved beyond prototyping, applications of additive manufacturing to more, the end-to-end different aspects of the product, even in manufacturing. So, Dominic, I was wondering, can you give us some examples of where you are now, using this technology, beyond prototyping?
Yeah, I think like what Ali said, additive manufacturing can be used in many different aspects. Still doing a lot of prototyping today. Still looking at some opportunities and some wins of putting it into our commercial vehicles. But ultimately, it's changing the way that we develop new products and accelerate our development time. Some examples are cutting out tooling costs from our pre-production vehicle builds, cutting a lot of capital out of that by direct printing parts in pre-production vehicles. And another very big space is manufacturing tooling, right? We have a lot less requirements from a validation standpoint with bringing a new technology into manufacturing tooling. And we can very simply implement lighter weight, lower cost, and quicker to manufacture components within our assembly tooling space.
Great, thanks. So that is useful. So basically, from prototyping, you're now more into tooling. Are there any examples that you're also kind of using this technology in serial production?
In terms of serial production usage, General Motors is actively pursuing opportunities to use additive manufacturing when it comes to low volume production of components. So there's certain vehicle platforms, certain vehicle programs that have volumes that are in tune with current capabilities of additive manufacturing that make economic sense and performance sense. Beyond that, looking at opportunities in other specialty use cases, such as service components, such as accessories, such as motorsports and racing programs. These are all opportunities where additive can shine. It can add value beyond just cost and timing benefits, but actually performance of the parts as well. As the capability of additive grows, right, as we get better, faster, cheaper with those components, we can certainly look to see expanded usage of additive in serial production programs at higher volumes in different vehicle programs and platforms.
So Ali, I would actually kind of now try to get your views for our learners on how do you describe the ecosystem around additive manufacturing, because it's an emerging technology and there are so many different players, right? How do you identify who are the major players here in terms of not the name of the companies, but first in terms of the function that they do?
Yeah, absolutely. So the entire ecosystem, especially for additive being a digital-based manufacturing technology, it is pretty broad. And there's many different categories. Of course, you have the actual machine OEMs or the machine vendors that produce the piece of capital equipment. Then you have the material providers, which in additive is a unique case of the machine vendors are typically the people you can also buy material from and sometimes have to buy material from for your equipment. Then there's obviously part suppliers, people that can actually produce parts for you if you're not producing them yourself. And these can range from traditional suppliers in the automotive industry, say a tier 1 or tier 2 supplier, or it can be new suppliers that are using additive in other industries and are now looking to grow into automotive as well. So these are sometimes known as service bureaus. And we look to develop these suppliers through our qualification process or technically approved source list into brand new tier 1, tier 2 automotive suppliers. You can continue moving into people that are providing services, right? So there's a lot of post-processing that happens to these additive manufacturing components, things from traditional machining and heat treating for metal components, all the way through to finishing plastic components the way you need them to use in your product. So there's a whole ecosystem out there of people that will finish the parts for you as well, often merged into the part supply chain as well. And then finally, the digital side of things is not to be forgotten. So the software ecosystem for helping you design the components right, for helping you print components correctly, simulate the components that you're about to print and their performance and their manufacturing simulation, and then manage the entire workflow and ecosystem of, say, a manufacturing execution software and the data pedigree that goes with that as well, being able to control the quality data and the data. So there's a variety of software vendors out there that comprise the additive manufacturing space as well, leading to the full digital thread, the full digital supply chain capabilities. So many different players, and any company looking to get into additive manufacturing needs to be at least aware of, if not actively involved in, developing all aspects of that supply chain and ecosystem.
So the knowledge piece, just continuing on that. So certainly, as you mentioned, they need to know, what kind of material should I use and what kind of process of additive manufacturing should I use. In addition to that, I mean, do they need to also have awareness about is there any software platform that needs to be used for that? What are the system integrated companies who work on this, or companies like Siemens? How do they kind of build knowledge around this? I mean, the ecosystem of who are the players in this?
Yeah, so that's a good question, because there are, as with many newer areas and technologies, there are a lot of niche players right now who have little bits of the secret sauce, that everybody needs to put these things together. Siemens is a pretty large company, and so we spend a lot of time tackling hard problems like, integrating the end-to-end solution for additive. So from the design through the simulation all the way down to printing. That's what we spend a lot of our time working on, because we feel like the integration of all those tools is what allows you to really have a well managed process that will get you to production with this technology. But there are a lot of smaller companies that have little pieces of the puzzle. And again, it kind of depends on the processes you're using, what you're doing with them. So if you're prototyping, maybe you buy a bunch of those small desktop printers and you allow people to use those all throughout your company to make small, inexpensive prototypes. And you're going to use little pieces of, mostly free software to do that. It's when you get to things like production that you need much heftier lifting on the software side and the hardware side to make those things a reality, to make them viable for a company to use. And that's when you'll need to start looking at other companies like Materialize or ourselves for the various different pieces of that workflow to fit those parts together into something that you can use to, take apart from its initial design all the way through to its print.
John, you mentioned that you work on 3 platforms in additive, right? I mean, and so, I have a couple of questions related to that. First, can you give an overview of the ecosystem of additive manufacturing as you see it, in terms of who are the different kinds of players? And then my second question is, what will be your advice to, companies who are beginning to think about adopting additive technologies and, prepare their organization to build this as a capability?
Yeah, absolutely. So I think it's a great question. And I see the additive market as, I really think about it split by kind of core material in terms of polymers and metals. So that's kind of the first high level split for me. And the reason that I think that's salient is there's lots of innovation taking place in both of those classes. But I think some of them, I would say the polymers, for example, or I'll start with polymers. Polymers, there's been a lot of advancements over the last 5 years in terms of new startups like Carbon 3D, for example, or more older kind of technology companies like HP getting into the game. There's been a lot of advances that have kind of are using fundamentally different ways, fundamentally different science of producing the parts that have driven orders of magnitude decrease in costs and increase in part performance. And so on the polymer side, and we're really just starting to see this wave of products hitting the market. But on the polymer side, I would say there's a lot wider aperture in terms of number of industries where it makes sense from a business standpoint. we're seeing a wide variety of industries. So that's kind of on the polymer side. And then on the metal side, there's kind of a core, it's a laser powder bed fusion technology. There's a dozen different technologies, on both material sides. But on metal, the core one is essentially a laser, that is melting powder in a very, defined and fine line, and then kind of repeating that again and again. And that's been really the main metals production method. And it is, it produces extremely high quality parts, and is also still quite expensive relatively. And so that's why we see it's really medical devices, aerospace, and just starting into some high-end automotive, kind of very, parts where there's really high value density, in a part. That's where metal is really making sense. And so that's why you see it's mainly medical device companies, in aerospace that have been really focused on that, and very successful, and absolutely very successful application areas. But we're still waiting to see kind of that cost threshold really drastically decrease and to open up the aperture of applications. There's been some exciting advancements on the metal side with binder jetting. Desktop Metal is one that's made a lot of waves as a startup in this space. But also GE is building one, and there are a few others. But those parts are still, those are very small, very tiny. It's essentially a metal injection molding replacement. So it's not, it's still waiting on that sweet spot of metals technology that will kind of hit I'll call it, Apple size part, or, size of a softball, where it starts to make sense. If I was to think about advice for companies starting to look at additive, I think the biggest way that I encourage folks to do it is, identify someone that is excited and passionate about it, because it will be tough, and so you need someone that's going to have some excitement about it. And then, identify some potential parts, have a workshop with, someone who knows something, could be with us, doesn't have to be, but, and, within a couple hours of, some, outside help or guidance, I think you could come up with a concrete list of ideas that you could then go pursue. And I think you could whittle stuff down pretty quickly. But I think the first thing is to really get someone who knows something that can be helpful to whittle it down, because it's very easy to go on wild goose chases. It's very easy to get excited about something, but there's no way it makes sense from an economics or part performance perspective. So, and then just start making parts, and testing them. And the good news is that the very, doesn't need to, there's very few fixed costs if you're getting parts, from a service provider. And so, start to get parts made, start to test out the materials, start to think about validating materials, to be used. And so that's how I would think about starting it.
So, John, thanks for that, explanation. But I was also wondering, you have the printer manufacturers, then you have material people that you actually kind of mentioned the two. Who are the other players? Like, there are the consulting companies, there are service providers, and this seems to be evolving. There's a lot of startup play too, correct?
Mm-hmm. Yeah, absolutely. So, I'd say across, startups, what I would call maybe the legacy additive companies, the ones that were kind of founded in the 80s and 90s. And then as well as some of the, the larger Fortune 500 type companies, I kind of think about the players in the ecosystem. So like you mentioned, there's the materials companies, there's the machinery companies, so the ones actually creating the platforms. There's also a a growing ecosystem of post-production machinery. So not necessarily the printers themselves, but ones that dye the parts or clean the parts or something like that. And then there's consulting. So there are consultancies out there that will help to advise on additive, both independent and also parts of other companies. And then there are services companies that kind of package this all up and provide customers kind of the bridge to customers to access all of that. And that's what we do primarily. And then the last is I'd say is software. And while I would say there's some additive, there's certainly plenty of additive specific software. I would say also, what is really enabling this is, like I mentioned earlier, just the innovations in digital design and how easy it now is becoming for entry-level designers and engineers to start to pick up and design quite complex structures. So that's how I think about the ecosystem of players.
In this section, we will be discussing the broader benefits that comes from additive manufacturing, broader business benefits. Before we get there, I think we want to recall that additive manufacturing is a broader term, like 3D printing, which actually a lot about the printing stage or the manufacturing of that particular part or the shape. But additive manufacturing, as we discussed earlier, it's kind of a broader umbrella concept which brings in changes to the design process, the manufacturing process, testing, and sometimes even in logistics, it actually changes and delivery to the customers. So let's look at this simple. I've kind of captured the broader business benefits from additive manufacturing in these 5 dimensions. There are also other dimensions we can add, but these I thought were some of the prominent ones that kind of come first in the list. First, these 5 dimensions. Productivity, quality, cycle time, customer experience. And I think the important one in additive manufacturing is the sustainability. The one in green, because additive manufacturing has a big contribution in terms of reduction of in the consumption of materials and reduction of waste, and that has significant impact. So let's go through one by one each of these dimensions in terms of what kind of benefits we can get or the additive manufacturing promises or brings to the manufacturers. So on the productivity, certainly we talked about faster prototypes, and then we can, if you can speed up the process of creating prototypes, then what that does is basically eliminate resources that actually you often use in multiple iterations, which are now avoided, and that elimination of resources leads to productivity benefits, right? And the same thing happens even on the production side, where you actually kind of not just the prototype, also the new product development itself. When you use some of the additive manufacturing techniques for some parts, it can shrink the overall time end to end. And then the direct savings from scrap and waste. And this is a very important savings that comes from additive manufacturing, especially if you can use, in some cases, the additive manufacturing in industrial serial production. Then, basically the traditional manufacturing, as we understood, the subtractive manufacturing, creates enormous amount of waste. And that particular scrap or waste is saved in the additive manufacturing. And that, savings and wastage obviously is not just savings coming from just the material saved, but you should remember that, as I mentioned earlier, in industrial manufacturing setup, there is a significant resources and cost and human effort, time involved in getting rid of that scrap and then recycling that scrap and so on and so forth. All those efforts and all those resources are saved. And there is also the third, in additive manufacturing, there is always a possibility of reducing material consumption. As we saw in some of the examples that I went through, that consumption of material obviously reduces cost and improving productivity of manufacturing. And the next point about cost reduction from alternative materials. Sometimes in 3D, when you use 3D printing or additive manufacturing as a concept, you may take an existing part, you can actually scan that part, understand the structure, the material structure and the strength of that part, how it is kind of designed. Then you can extract the design information and the design constraint expectations out of that. And then you may actually search for a new material. Sometimes, companies actually take a metal part and then get it, re-engineered and then get it reverse engineered to understand the design and come out with a new design with a different material. And that alternative material may be cost-wise and expensive, may be reduced in volume, and that can bring efficiency benefits and productivity benefits. And finally, last but not the least, the consolidation of parts into one part, right? We saw that in the earlier example of that burner example of 13 parts to one part. Next, look at the important dimension of quality. Quality, as we all know, is such an important dimension in manufacturing. Manufacturers spend a lot of resources, time in kind of preparing the process for quality, training their employees for quality. The entire lean approach is a lot focused on quality and productivity, right? But additive manufacturing actually brings some new capabilities and new features that actually helps manufacturers manage and improve quality. At the same time, also brings a new perspective for manufacturers to look at how they manage quality. First, the process of additive manufacturing, basically what it does is it is reducing drastically human intervention in the making of the part, right? As we understood, parts are actually 3D printed, correct? That means you don't have much manual intervention there. When you reduce the manual intervention drastically like that, what happens? Basically, the variability that comes from manual intervention that goes down. Remember, in all the quality improvement initiatives, right? I mean, like the famous ones like Six Sigma. Now, the Six Sigma, training that happens in large manufacturing companies, that's because Six Sigma means they want to kind of reduce the variance. They want to almost make no defects at all, no kind of deviation from the compliance requirement for that particular part, right? So that's what they're trying to achieve. They're trying to achieve that by training people, by tuning machines. That's what they're trying to do. But 3D printing, because it is totally automated, once you have the right design files, and if you use the same printer, right, then it doesn't matter whether you are actually printing or creating that part through additive manufacturing, either in Detroit, Chicago, in Shanghai, in Mumbai, and it doesn't matter where you're producing it. It also doesn't matter who's producing it because the human intervention is reduced. And that has a significant impact in terms of improving quality. And this consistency that actually comes with additive manufacturing certainly also adds to productivity, and also it reduces efforts that are required in testing and things like that, right? And finally, the capability to verify quality at the time when the product is built. Often, what we see is that, we make in the traditional manufacturing, there is manufacturing, producing the part, manufacturing the part is one stage. And often the quality inspection is a stage after manufacturing, right? It's an afterthought process where once the product is manufactured, there is an inspection stage where the quality, if the products are, inspected for quality. In this additive manufacturing, now you know the material, through design, exactly how the material is supposed to behave, how it's being printed. You can also, put scanners. We can actually observe the materials as it's being printed. And then from there, through the computer vision, you can actually look at any deviations and you can detect the quality problems as printing is happening. In other words, there is a capability to verify the quality at the same time when the product is being built. And that's a completely a new, feature which actually helps manufacturers improve their quality. Next, cycle time, another important component of how we understand business benefits in manufacturing, right? Additive manufacturing, through rapid prototyping, drastically reduces anything that you want to make, whether it is parts or tools. That reduces your time. And then this ability to consolidate parts that we talked earlier. Now, we talked about the consolidation of parts and then in terms of productivity. Now, think in terms of cycle time. If you take that one example of from 13 parts to one part, or in the GE helicopter example that we saw, they're combining about 30-40 parts into one part that is being additive manufactured, right? In that case, what is going to happen is you have to take into account the time it would have taken for those multiple parts to be individually produced, manufactured in the traditional way, and then combined, first tested for quality, each individual part, and then combined, assembled, further test again, right? all this time they may be kind of saved. And that's why this integrated end-to-end time saving in additive manufacturing promises are quite impressive. And the last part about the capacity for distributed printing in additive manufacturing. What I mean by this distributed printing, like if you adopt, if a manufacturer adopts additive manufacturing, then what happens is then you have the design information, design file in digital format, right? That means you can ship the digital file into any other location, right? Any geographically different location, and they can actually print it there, near the customer, near wherever the part is required. Then this is the distributed printing capability. It is not 100% there as yet. It's not yet there for industrial manufacturing, but the idea is now shown in what I call as the consumer 3D printing, where people are using it for fun and print their shoes and toys and things like that. But as this capability matures, and if it comes to the industrial production, then we are talking about an automobile manufacturer, wanting a particular spare parts, can actually send the file to a dealer, and then the dealer can just print it there. Then what does that do? That actually saves the time and cost that is involved in logistics, right, of getting the parts from one place to another. That's another important potential saving that can come in terms of time and productivity from additive manufacturing. Let's look at the next dimension, which is about customer experience. Additive manufacturing actually brings that critical capability. We all talked about how the manufacturing industry is changing. In the beginning of this course, of the series, we heard from some of the senior manufacturing executives as well, confirming that there is more and more demand from the consumers for personalization, right? Or n equal to 1 sample size of 1, or in manufacturing terms, lot size of 1. Additive manufacturing actually brings this capability to the manufacturers, where if there is a market, if there is a need, and consumers are willing to pay the price premium, additive manufacturing easily enables manufacturers to do this, lot size of 1 in an efficient way, as we discussed earlier. This technology also brings other benefits to the customer in terms of enhancing their experience, because additive manufacturing can actually, improve the product strength, performance in terms of strength, weight, and so there are so many other parameters in which the manufacturer can actually tune and design the product or a part in a way that it is much more, kind of closer to aligning with what the customers really want. In fact, if you talk about customer experience, one of the big changes that is happening, in the adoption of additive manufacturing, or more, I would say not exactly as we understand as it is, it is being used as additive manufacturing now, but I'm also talking about what is coming in this technology space, right? So in additive manufacturing, what happens is there is now an opportunity for consumers and their manufacturers, right? Customers and the manufacturers to sit together and jointly co-create the product that they really want. Often the manufacturing industry, the way it is worked is the following way, right? Manufacturers try to understand the customer needs through focus groups and things like that. They bring a group of customers into the room, deep dive into analysis, and then kind of understanding their requirements, deep dive interviews and all the stuff. There are so many marketing techniques of engaging with customers to understand their needs. They actually collect all that information and then come back to the drawing room, and then they design a manufactured product that exactly what should be the product, right? However, in that process, they certainly may compromise, right? Some of the design constraints, some of the kind of cost constraints. They compromise to, of what is possible. If what the customers really want was a big circle, then what is delivered is often a smaller circle, which actually kind of meeting some of those requirements. Now, in additive manufacturing, because the design being digital, it actually enables, especially in a B2B context, with industrial manufacturing, the manufacturer and their customers can actually sit down together and deeply understand where exactly this part is being used, where is this product being used, what is the end customer use, and what are the requirements, and they can actually map that to the design, experiments that they're actually creating, and how they're using algorithms to explore the design space. They can bring that information and hence optimize the design for the use that it is being put to. Then that actually enhances the customer experience. And the last but not the least, in fact, one of the most important benefits that comes with additive manufacturing is sustainability. As discussed earlier, reduction in wastage, reduction in scrap, right, compared to traditional manufacturing, automatically, makes the process much more sustainable, makes, you reduce wastage. Obviously, you're actually kind of reducing not just the consumption of material, you're also eliminating the process, energy usage for consumption of the materials. All that is eliminated. I mean, obviously, certainly making the manufacturer more greener. And design optimization for material consumption, right, which is basically sometimes, as we, some of the examples we saw, additive manufacturing, design optimization leads to reduction in material usage, and that leads to, more greener process in terms of, consumption of materials. Sometimes additive manufacturing also helps manufacturers to look at an existing part and then look at, alternative materials. They often they have an opportunity to choose green materials, which even in their design and creation of those materials kind of eliminate or reduce, emission of greenhouse gases. That actually makes it entire process end-to-end much more sustainable. So overall, the reduction of resources, right in the end-to-end supply chain, if you think additive manufacturing being used, and that actually has enormous benefits. First an end-to-end supply chain, and then coming into a manufacturer, possible changes in the design stage, in the production stage, in the testing stage. What we talked about, all these examples and all these dimensions, we are eliminating resources, we are eliminating steps, we are reducing time, we are shrinking the cycle time. All this leads to, of course, reduction in the consumption of materials, resources, reduction in elimination of operations. All these things combined, create enormous benefit in terms of making that manufacturer greener. So in summary, we have looked at the business value benefits from additive manufacturing across all these 5 dimensions. Obviously, the dimensions that we talked about here are interrelated, and as the process of design, production or manufacturing, testing, logistics, everything is being altered by additive manufacturing. You see this enormous potential for benefits in all these 5 dimensions, especially all of them leading to sustainability and making the manufacturing process much greener.
Actually, beyond the advantages of dealing with complexity and bringing this new intelligence to the products, can you tell us about the sustainability benefits, like the carbon footprint and environmentally friendly, we hear, the additive manufacturing processes? Can you explain a little bit more how that is and what kind of benefits that we can expect?
In general, speaking in generalities here, additive manufacturing is often found to be a less energy-intensive manufacturing method than, say, machining. In many cases, you can generate, a part for less energy than it would take to machine it. But that's just kind of the tip of the iceberg sort of thing. There are lots of ways additive helps with the environment. So one of those is through materials. There's a high rate of reuse of materials in additive. So when you have this big vat of powdered material, you're only using 2% of that fused together to make your part. The leftover material immediately gets pushed back into the system, mixed with some percentage of virgin material and reused. So additive is a fairly efficient process in that regard as far as the material it uses. For example, if you're machining something, you're going to generate a lot of scrap, all those shavings, but those shavings have to be sent off to a facility for processing. That processing takes a lot of time. The shipping of that material to that processing plant and back again takes energy. And so that whole recycling process is sort of cut off with additive. You're recycling within your own facility, using, again, material that's been used in a print before, leftover material with new virgin material in a combination to basically induce recycling within the process itself. But that's just, again, one part of it. The printing of the part, the making of the part is one way additive can help save energy. But I think maybe even more importantly is the efficiencies we've talked about from the parts that can be made with additive. So when I'm shooting, let's say, a satellite into space, and I can save a pound of weight. That is a ton of fuel. I mean, it takes a lot to fire a pound of weight through our atmosphere. It takes a lot to fly a pound of weight from Los Angeles to Paris. All of those things are very energy intensive tasks, and making parts more efficient, lighter, using additive allows us to use less of those that energy later on when those products are used out in the field. So you can imagine, the printing being one little kind of starter way of additive helping the environment. But when those parts get out in the field, it multiplies, and additive can really be a game changer when it comes to things like reducing weight, allowing things to be aerodynamic and structures like that. So I think the potential for additive to be something that helps us with our environmental problems is huge.
Great. So that is very useful. Thank you. So when you talked about the business case, right? When you go up with the business case, are you able to kind of project in terms of what the benefits would be even before you start the project, or how does it work?
Yeah. So it's a great question. We have a framework, we call it the total value of additive, where we help the customers think through the different levers, in terms of cost savings, cost avoidance, potential revenue uplift. And so, what we will do with our customers is help them think through that framework, and also think through, who do you then go to get that information? So, and how do you help to build a business case? Because especially, I would say, when it's more, as our customers tend to be the engineers and operations type folks in that function, if the opportunity is, let's say, part consolidation, where you've got a part or an assembly and you want to turn it into something monolithic. So you print one piece instead of 50 components that get screwed in together. The engineer can go and get that information, from their team and understand, okay, what are the costs? What kind of field issues are there, potential yield issues that we can eliminate in the factory with the assembly? Are there field issues that we can eliminate by having a single part? I would say when we start to get to new, kind of more pure new product development. So the Rawlings example is a great one where we produce an insert that goes in their new high-end baseball glove. Provides better performance. That's where it truly is the product marketers and the product team that really come in, and they have to make a business case. But ultimately, if it's a new product that's going to drive additional revenue, they do have to make a bet. And they obviously will go with them on the journey, and that's part of what we do is moving fast and creating small volume or small batch runs that the customer can then go and do field testing, and go do testing with customers, because it's essentially a part that's the quality of the finished product. And so they can get that in the field quickly and test. So I'd say, to sum up, the answer to your question, I would say it depends a little bit on the value drivers, whether it's a more pure cost-oriented play or whether it's more revenue uplift.
So, John, thanks for throwing light on that. How do you think about the business value of additive? But a lot of times, when people compare additive manufacturing to traditional manufacturing, and the cost-wise, tend to compare how much does it cost, manufacturing the traditional way as compared to additive. But with your business model or the business case, creation, that do you see the entire end-to-end value chain benefits of moving to additive? Because you actually tend to benefit on the design side, of course, on the manufacturing, piece, and I would believe even in quality and inspections, is it not?
Yeah. So as we think about what drives what drives the kind of the overall business value of deploying additive. I think I think you've hit on a lot of things, and if it's used, if it's really driven, effectively, it really affects all aspects, kind of end to end. From upfront, additive enables a lot more design freedom. You can make a lot more kind of natural shapes. You're not as constrained. And so, on the design side, it actually enables a lot more freedom to design kind of what's in your head versus having to then kind of constrain it more for manufacturing. Of course, there's still manufacturing constraints, but there's a lot, there's fewer, I would say. And then of course there's our customers that have embraced additive the most in terms of training their engineers, and really getting their engineers to understand how to use also new tools of this digital design, like generative design, for example, is one that gets a lot of attention and excitement. And so those companies can then drive also innovation a lot faster because they can drive faster throughput with their designers, and it's really then starts to blur the line with manufacturing engineering, because the additive does, while it does have as I mentioned, it still has kind of manufacturing design requirements. You have more freedom, and so you can allow these design engineers to really get their parts designed and back to them very quickly. And so you're driving speed on that front, and reducing the cost as well. And then as we think about also tooling up and avoiding those costs, it's actually an interesting challenge that some of our customers have, which is the procurement folks and the buyers are incentivized on piece part price, and the tooling is a capital expense that can be someone else's budget. And so when an additive, you're typically your piece part is if you're looking at a piece part price versus injection molding is going to be cheaper. But if you fold in the cost of the tool, that's when you start to make the business case, and that's where we're seeing the break even point, so to speak, from 1,000 to 5,000 4 years ago to like the Additive case I mentioned earlier is in the tens of thousands, and that's what enabled the shift to additive there. And so then it's building the business case and making sure that all the incentives are appropriately aligned across the business, and then as well as we start to think about end of life, and being able to produce more on demand, you have additive qualified, is qualifying a manufacturing process for a part cost. There's a fixed cost for that. And so additive has been qualified. And so now all of a sudden, as you're going back down in the end of life, or kind of back down on the product life cycle, you can switch to a more on-demand production method. So you're not doing a last time buy, or maintaining inventory. So we see benefits across I'd say the full product life cycle, definitely.
In this section, we will be discussing implementation of additive manufacturing in both large and small manufacturing organizations. While the promises that additive manufacturing brings are impressive, and we also seen many success stories, but if you look at in the market, you would see that just like any other technology, the kind of there'll be full spectrum of experiences with additive manufacturing. In some cases, they would see this as a bigger hype, and then they would not have realized the business benefits. And in some manufacturing organizations, you may see that additive manufacturing is more like an experiment, and not only just one experiment in different plants and different units, they're all experimenting. There's a lot of experimentation going on, but the end product that are finished and then used in production, either in the prototyping or production, or not as much as the investment that has gone into additive manufacturing. That's one challenge. There is also, cases you would find that there is kind of siloed additive experiments that are going on in the R&D. They've shown some success, but it's not been brought into production. That's another possibility. I think there is so many reasons why we see mixed success, and I believe that every organization need to have an explicit additive manufacturing strategy, and they should have a methodical way of managing this implementation, because this is a new technology and this is a new approach to manufacturing, which fundamentally challenges, it's quite different from the traditional manufacturing. So obviously there will be inertia, there will be pushback, and so this has to be evangelized. The organizations have to build trust inside to kind of for this additive manufacturing as a concept to take off. So what we have here is I've got a simple 6-step process that companies can use, or kind of which actually captures some of the challenges that are faced and how companies can take actions in order to mitigate any risks of this technology being left just in the experimental stage and not going to the production. So let's look at this framework, which is a simple 6-step framework I call, where you first identify the problem that you're trying to solve and then create the business case that the additive manufacturing is bringing. Then how do you build the capability around this technology? Then third is, how do you, the importance of identifying a sponsor and working with the sponsor to make this execution successful. And then there is, step number 4 is about alignment and building a partnership within the company, right? There's so many, and additive manufacturing is another example where it's not about one particular unit of manufacturing. It actually kind of touches design, manufacturing, testing, quality inspection. There's so many kind of different units within the manufacturing organization that may get affected. So you need to kind of build that partnership. And then talking about partnership, the 5th step is about the broader ecosystem of external partners and internal partners. How do you put them all together to set up for success? And finally, how do you kind of manage the execution and then help scale this experimentation in additive manufacturing? So let's go through step by step, each of these steps in terms of what does it mean and how do you apply this in the context of additive manufacturing as a technology. In the first step in identification, I think, it is important for manufacturers to kind of, if they are starting with additive manufacturing, to look at broadly survey, what are the kind of parts, specific parts that may be candidate for additive manufacturing. Then, as we learned in this course about the different criteria for additive manufacturing, where it works, where it kind of fits with the kind of advantages of additive manufacturing, we need to see if these parts are actually fitting those criteria, and that needs to be identified. Then, of course, selection of the site is also important because additive manufacturing actually calls for a different talent base, right? I mean, it's kind of it cuts across discipline, and so it is important for organization to select the strategically chosen sites to start experimentation, so that they can set up for better success, better chances of success in the future. The next step is building the capabilities for additive manufacturing, right? As I mentioned before, it is they have to kind of build a strategy for additive manufacturing that involves resources, that involves human capital, and that involves completely rethinking the process. And they need to kind of build a core set of capabilities, right, around the additive manufacturing capabilities, including not just think about 3D printing or about printing a 3D object or a product, right? They need to rethink how they think about design, modeling a design, exploring design space, so design optimization. They need to bring together skills that is in the intersection of computer science, material science, operations, manufacturing engineering, so that what we traditionally saw engineering and design is actually combined with the digitization here. So these different kind of skills, teams with these backgrounds are coming together to work jointly. So companies need to think about this requirement and then organize according to these skills and organize according to the problem to be solved. In some sense, they actually kind of need to set up some center for excellence for additive manufacturing, so which actually kind of not only supports additive manufacturing projects, but also learns from each of the projects so that you have the common database, a common knowledge base that is actually kind of collected. And also you're able to identify human resources and people who are actually evangelists and champions of this technology. Because as I said again, this is a new technology, may not be always accepted readily by all engineers and plant managers and operations people, because they are all kind of very used to the traditional way of manufacturing. They see the strength of traditional approach to manufacturing. So you have to kind of build that momentum through this Center for Excellence in Additive Manufacturing, which is a collection of knowledge base, people expertise, and also investment in tools and technology. The next step is the sponsor. Certainly, you have to kind of identify an executive sponsor, right? I mean, who actually has to be behind this project. Suppose, say, you're actually picking a specific part, as you've identified a part that you're going to experiment with additive manufacturing. Then you have to look at, who should be the right executive sponsor. Then you need to identify all the stakeholders, internal stakeholders of that particular part or product, like including the current operation team and the customers who are going to be using the part, the design team who actually designed the original part, so that you understand exactly, why they designed it that way and what are the kind of performance parameters of the part. And also, of course, bring in both the new team and the old team together to understand the problem that is being solved. The point I want to make is, looking at additive manufacturing is not about just looking at one part and then say, well, I'm now making it from injection molding or die casting, and then I want to actually use 3D printing and print it. And how do I do that? I think, instead of taking that approach, I think what companies need to do is that they need to look at this broader set of capabilities that additive manufacturing brings in terms of exploring the design space. You understand the broader problem that you're trying to solve. What is the function of this part? Why is it designed like this? What is the actual usage by the customer? So that you understand the design requirements, right, of this part, and then you put that into the algorithm so that you can explore the design space, and you may actually come out with a completely different design, which may be better than the current design, and that's an opportunity should not be missed. And of course, after that, you need to create a business case for the overall additive manufacturing process for that part, in terms of what are the potential savings that we could get in materials, and in terms of performance, quality, and so on and so forth. That the kind of different dimensions we talked about earlier in the course. And then look at the applicability of the current assets. Like when you're moving to make choices in terms of really kind of adopting that design and making the part through additive manufacturing, then you have to make sure that it's aligned. You're making use of current assets that you may have, whether it is in terms of printers and machines, or it is just a supplier relationship and supply chain, or your human capital. Make sure that it is aligned with that, as you kind of look at your approach to, adopting additive manufacturing for that particular part, so that you're actually incrementally building your capability and broadening, the knowledge base. And of course, the executive sponsor has to be very knowledgeable and also supportive to this, this attempt to kind of implement additive manufacturing.
Actually, you also mentioned, when you started with the challenges that companies face, you started with the biggest impediment is the knowledge, right? In addition to that, do you also see resistance to change from the organization? In some extent, like I'm just recalling an experience. I was working on a project, additive manufacturing project, a large manufacturing company and they had to really make a business case, and because there's a pushback and in terms of let go the traditional manufacturing for a particular context. Is this a unique one-off I saw, or do you see this in customers usually when you're thinking about additive manufacturing?
This is one of those things you have to kind of get through when any new groundbreaking disruptive technology comes around, right? You've got an established group of people who are used to doing things a certain way, and they know how to do that very, very well. And so they automatically feel like when you're introducing this new disruptive thing, I'm going to be less productive. I'm not going to be able to get my job done the way I need to. This is going to be more expensive, or this is going to take more time. And you have to work your way through all those issues with any disruptive technology. Additive is no different. We see this everywhere. And what we usually find is good for companies is when you have a new technology like this that you want to explore, it makes sense to put together kind of a center of competence where you gather up experts from various different parts of your organization. One person who's a design person, one person who maybe is good at simulation, one person who does the actual production down in your shop. And you get those people together and you start working through the possibilities of the technology, looking at the good things, the bad things that come along with it, looking at the places where you think you might struggle. And basically outlining a strategy for working your way through, this adoption of this new technology that you're pretty sure is going to affect you, but you don't know how yet, right? And so you get those experts together and they each bring their expertise to the problem, and you can kind of put together like I said, a center of competence where you now have people that understand what this new thing is and how it might affect your organization, and they can start to educate other people in your company or your organization about it. So we spend a lot of time with customers kind of either working with these centers of competence that they've already implemented or working to help them put together one of those so that they can, get through this sort of initial resistance period to this new disruptive technology.
Ashley, based on several years of experience working with multiple customers, what advice would you give for somebody thinking of starting their first additive manufacturing experiment or project inside the organization?
One of the things that we often recommend, and one of the reasons, well, let me rewind just a little bit. So one of the things that additive was used for very early on was they called it rapid prototyping because it was almost always used to make prototypes. And the reason it was used to make prototypes is because you need things fast, and prototypes are kind of low friction. If a prototype turns out wrong, it's not going to destroy your production run. It's not going to affect your delivery time for your end product or anything like that, right? So it allows you to experiment. And so we look for ways that companies we work with can learn about the additive manufacturing technology and experiment without impacting all of their business, right? So prototyping is a great way to do that. Start out by using additive as a prototyping tool. Many companies start that way. They get their feet dirty. They start to understand what they can do, right? And then they kind of scale up from there. But there are other things you can do too. So there's a lot of behind the scenes things that go into manufacturing products. So for example, as parts move down a production assembly line, they often are held in jigs or fixtures so that part's held steady and people can put screws in it or whatever the process happens to be. But those jigs and fixtures are not the final part, but they're part of that manufacturing process. And oftentimes you can use additive to make those. You can make them lighter. You can make them with less material. You can make them very fast. If a new process comes into play, you can build a new fixture for your assembly line really quickly using additive. So we recommend that our customers find areas like that where you're not impacting the final product. You're doing something behind the scenes that supports that final manufacturing. And that allows you to get your feet wet, to try out the technology, to learn a lot about it, that knowledge acquisition we were talking about earlier, without the risk that you would have going straight for trying to print a final product, right? So that's one way that we think is really, really useful for companies that are just getting started, is to find those applications where the risk is low and the learning is high.
The next comes the alignment stage, where in alignment, you're now looking at not just the internal partners. Now you know that this is kind of the problem you want to solve, this is the part you want to make. Then you actually look at, all the design possibilities, you considered some of them. Now it's a time to look at who are the external partners. Now we talked about the ecosystem of additive manufacturing. You look at the ecosystem and who are my partners in design software platform, or who are the partners in 3D printers, or do we use the 3D printers that we already have? Is that the better option to go, right? And then who are the material suppliers? Am I going to leverage the current material suppliers, or do I need new material that actually brings some special business value for this part? And so those things have to be considered, and then look at if you want to work with any consulting company or integration partners. That's also important. And of course, the last point is that you need to identify in all the changes required in the process, right? Because if you are taking manufacturing of a particular part from a traditional manufacturing to additive manufacturing, as we discussed earlier, that can significantly change the operations, right? I mean, you may not need the kind of line that you have that you had already. You may not require the number of people that were actually kind of engaged in the traditional manufacturing process. So if those are going to change, you need to understand what are these changes in process, in behaviors, in people skills. And in some cases, you may end up eliminating some of the roles. And that doesn't mean that you eliminate the jobs or get rid of people, but then you see how do you reskill them? How do you redeploy them? All these things have to be thought through, and also what are the new skills that are required that people need to be trained when you kind of move to additive manufacturing. The next one is in partnering, right? And this is where you actually are now, finalizing the partnership, because now you thought about what the future processes are going to be. This is going to be the printer, this is going to be the platform, and then this is going to be the material I'm going to use. And then here you need to also make sure that not only external partners, you also look at internal partners, right? You know what I mean? If you're moving to additive manufacturing, then you want to make sure that it is in alignment with the PLM software, the product lifecycle management software that you're using in the organization. It is kind of connected with the ERP software, because of course this is finally going to be connected to the business operations of the manufacturing business, right? You need to make sure those alignments are there, or at least think through this and how it will be achieved. And then also, before you start executing the next step, you need to make sure that there is a change management, program in place. How are you going to communicate this new change that you're putting in terms of additive manufacturing? How are you going to communicate why you're doing this? What is in it for each of the parties that are impacted, so that you can set up for, better set up for success. And the final step is about execution, right? I mean, when you implement the solution, then execution is a key part, where you build and test the part for overall performance. If you want to iterate in terms of different parameters, and then make sure that the business case, whatever is promised, is aligned, or in terms of what is delivered, in the end product, and look at that. Make sure that the required training. If people have to be trained in a different way in terms of managing this entire additive manufacturing process, that should be taken care of. And then you roll out the pilot production of the part, and evaluate and collect the metrics in terms of whether it meets a business case promises and the dimensions of success that were defined earlier, and then reiterate if it's not. And then if it's successful, then you plan with the executive sponsor to kind of announce and communicate the success, and then plan for scaling this to other plants and potentially for other parts as well. So basically, what you need to do is that you need to take, each step is a learning mechanism, it's a learning step, so that each one of these projects, you see what you learn from the additive manufacturing experience, what worked, what did not work, and take that knowledge base, contribute towards that, the Center for Excellence we talked about earlier, so that you are over time kind of creating a repository of cases, so that you're building the organization, and setting it up for future, so that they can be more successful in adopting this, important technology. Actually, I would like to ask about some of your customer experiences. Certainly, you've been working in this field for many years, and you have several experiences. Looking at your customers in going through this, implementation of this additive manufacturing technology. What are the typical challenges and risks they face in terms of when they try to experiment with this technology?
The biggest impediment that we see going through additive right now is just a general lack of knowledge. We've had, depending on which technology we're talking about, those legacy manufacturing technologies have had as many as a millennia worth of years for people to learn about how those technologies work, what it takes to make them efficient and successful in a manufacturing environment. Additive has come around fairly recently. We're talking about maybe a decade here that people have really talked about using additive for real production work. And so there's not a lot of knowledge just in the general populace yet, working with these tools and these machines, for companies to understand what's possible, how much is it going to cost me, how viable is this for what I need to do. So we're spending a lot of time with our customers just going through that knowledge acquisition process as the first part of their journey, so that they have to learn, what kinds of materials can I use, how much is this going to cost, how can I wring some efficiencies out of this process to make it work better for me, what's going to succeed and what's not. How do I get quality out of the process? There's all these sort of variables they have to work their way through. And we've seen lots of companies use different techniques for how to do that. For example, companies that do a lot of printing, so what we call, service providers, they're companies that are contracted to do printing of parts for other companies. Those companies usually specialize on a specific range of materials using a specific range of technologies. And that's one way they can limit the number of variables they have to deal with. So they'll print, aluminum and titanium, and they'll do it with printers just from one vendor so that they can basically crunch down the number of variables they have to deal with, learn those really well, so that they can perform in that small niche in a way that allows them to build a business around that. So there's a lot of that going on. But in the general marketplace, when companies are just starting out with additive, there's some techniques we can talk about for how to get started as well. But knowledge acquisition is definitely one of the main barriers at the moment for companies in general adopting additive as a technology for their business.
So, John, so with your experience, you've been in consulting, now you're kind of leading this startup, and, the way you've seen how additive and other technologies are changing manufacturing. So what will be your advice to our learners who are either in the manufacturing industry already or aspiring to build a career in manufacturing? What will be your advice to them?
Do it, or learn more. Manufacturing is important. For us at Fast Radius, we talk about making new things possible, for the world. And, and for me, manufacturing is not just, the parts or the little components or little widgets, but it's what those parts and components and widgets enable. It's, the medical devices, that keep you healthy. It is the, cars that deliver you safely to where you need to go. It's the sporting goods that let you have fun, out with your friends and kids and family. And so, for me, the physical world is extremely important. It's what we live in. And, I think there's a lot of excitement and innovation that is happening in the space. And I would encourage folks to, to check it out and learn and get understanding of all of the different, new innovations, happening in the area.
So to that point, John, certainly the way digital technologies are changing manufacturing, right? Am I right that, traditionally manufacturing, we had very predefined roles, right? You had an engineering designer, your operations manager. You have different roles or design. We're kind of very determined, and that's been there for many years, right? Because traditional manufacturing existed for, decades. So in the digital world, right, do you see this more multifaceted talent? And, where do you see is the, demand for talent here? What kind of is it evolving? Yeah.
Oh, yeah, it's a great question. I would say it's across the spectrum of the people, that work for Fast Radius, from our, design engineers on the front end. They're using design software where they're essentially coding they're essentially coding the designs. They're not kind of creating blocks and then subtracting or adding or extruding. They're essentially creating code that is telling the software engine to generate these shapes, the desired shapes. And so, which then enables much more flexible designs, and it's much easier and all that kind of fun stuff. But, it is our mechanical and design engineers are, they know how to code, and they are coding. And so, that too, our frontline technicians that are, running the prints, we need them. They're interfacing with a software system, our software system that we've built, but then we're also asking them, for, input, on it, and they need to understand, how to use an app on the phones, the tablets we provide. There's kind of a level of skill that's needed on that front. And then even to our salespeople, understanding how to use our software to get customers the answers they need, whether on design feedback or something like that. And so it is certainly blurring. It is enabling a lot of the digital innovation is also essentially putting what used to be in very smart individual contributors' brains. It's putting that into code. And so it really is blurring the lines, because now all of a sudden you have lots of people that can access that, that knowledge. It gives them superpowers. And so it enables them to be more, productive and with what they do. And so certainly I'd say the lines are very blurry, across functions.
So Dominic, based on your years of experience, deploying additive manufacturing capabilities and at General Motors, what if I ask you to carve out from your learnings in terms of if there is a new company or a new manufacturer wanting to build this capability, what will be your advice to them, and how should they approach this?
Thanks, Krishnan. I think in regards to adoption, the biggest challenge that we've had in General Motors is, and probably in a lot of large companies, is that we are somewhat of a well-oiled machine, standardized work, executing programs efficiently, and infiltrating new technologies, new capabilities, and new ways of doing business into that mindset can be difficult. And so we've taken an approach where we do a lot of proof of concept work, parallel path work alongside some of our standardized work to showcase capabilities. But ultimately, our goal internally is to teach the organization how to use it, not necessarily have only a small pocket of advanced technology users. But again, as Ali had said in the past, make it a tool in toolbox, make General Motors fluent in additive. And we have seen some successes with this through different manufacturing engineering groups, specifically with sand casting in Defiance, where now it is just part of their business to 3D print pre-production sandcast tools, with high pressure die cast metal tooling in Bedford, Indiana, where it is now just part of their business to source additively made parts. Every single die cast tool that runs at General Motors has a 3D printed part in it. And also in a lot of our assembly tooling and product development areas, it's becoming part of the business. So that is how we are infiltrating. And in regards to our supply chain, I think there's a duality of new manufacturers and existing automotive manufacturers. And Ali Shabir can comment on those.
Yeah, thanks, Dominic. So picking up from where Dom left off there, adopting additive manufacturing, small, medium, large size companies is always a challenge, and you have to understand what it is that you're going to try to use it for. You may not have all the answers right away, and so there is a little bit of this learning, this leap of faith that you need to make where you look at parallel industries or your competitors or people in similar markets and see how they might be using additive, and if you can feasibly use the same. General Motors went through that journey when our executives went around the world basically and understood in other verticals, other business markets, how they're using additive and saw the potential for it in their business as well, in the automotive General Motors business. And that leap of faith plus an executive champion is really what moves it forward to give you the initial momentum to go and mine some of those opportunities to prove out business cases in certain, sticky applications, right? Dominic highlighted a few on the manufacturing side within GM. And there's certainly many on the product side as well, where we look at a lot of our pre-production components and we're not so focused on making sure that it gets into serial production and miss all the low-hanging fruit that's around us in the pre-production space, the service components, et cetera. So really getting an executive buy-in and champion after going and seeing, understanding what additive is capable of and what potential impact it could have in your business, and then giving some people the freedom to go out and explore, right? Whether that's 6 months, 12 months, 18 months, whatever it might be, whatever horizon you set, to go find some of those sticky applications that gets the ball rolling. Simultaneous to that is what Dominic was saying around education, right? It's paramount that it's not just a pocket of specialized experts that are using additive. They're certainly going to be the lead users. They're going to be the ones that you want to understand it at an A+ on the final exam level. But they need to be able to teach the rest of the organization what it's capable of. You need to be working hand in hand with the engineering teams, the manufacturing teams, the sales marketing teams, whatever it may be, to help them understand, maybe not at an A+ level, but at a B+ level, at a B level, what the technology is capable of and what those applications are. And that's truly where you start to see the buy-in, where a team that's done something a certain way for decades sees a new way of doing things in maybe a parallel path fashion, and then starts to see the benefits, the business benefits that come with that, whether it's cost, timing, performance of the part, quality, and then the ball starts rolling from there. So it's really about getting that buy-in and adoption with some sticky applications that you work hand in hand with people within your organization. And for those small firms that are looking to adopt additive to ultimately develop parts or sell parts to customers, it's the same sort of deal. You become the experts. Go see, go understand, and go pitch it to your customers. Go help them understand and see the light and the business value proposition in their domains and for their components. And we actively push that with our supply base. General Motors, with our existing tier 1, tier 2 suppliers, encouraging them strongly to consider additive for General Motors programs and components. And then also bringing in new suppliers into the fold as well, existing AM experts, AM suppliers that can then come in and also teach those incumbent tier 1s how to use this, how to do this, and teach us a lot about additive too.
Like any other technology with promises, additive manufacturing also comes with risks and challenges. So let's look at some of the challenges and risks that may come with additive manufacturing. Well, in terms of challenges, like I've listed only 4 of them here. There kind of, many more, but let's just talk about, at least address some of these here. Technology and capability, right? As we talked about the ecosystem of additive manufacturing, there are many moving parts here. When you put an additive manufacturing, capability in place, you're depending upon materials, 3D printers, you're actually connecting it back to your PLM systems. There are multiple software that may be involved, right? Which and the compatibility of the software connecting, and then also the precision of the technology to work exactly as promised. And those are all some of the challenges. I think we are getting there much better than what it was 10 years back, but still this compatibility and putting it all together, and that has to be managed, and that's a challenge. Second is related to the material supply infrastructure. Now, as opposed to traditional manufacturing where we have very well defined supply chains, exactly, we know the tier 1, tier 2 supply chains, and they know their roles, and this has been there for centuries, right? So, in contrast to the traditional manufacturing, if you look at the supply chain in additive manufacturing, it's completely totally different, right? We are now looking for a completely new set of materials, and then you're relying on a reliable, reliable supplier for these materials. And not only that, I mean, you're also relying on the consistency from these suppliers. And so that are not kind of forgiven. You may have some disruption in these supply chains in terms of availability of these materials and things like that. So that's another challenge. The third piece is about awareness and capabilities. As we touched upon earlier, this is a new technology. This is a new concept to manufacturing, and although it has got a lot of potential, there are also still doubts, and sometimes it is hyped also. And hence, the acceptance of this inside large manufacturing organizations sometimes is questionable, in the sense for two reasons. One, there may be a genuine kind of doubt about whether this technology works the way it is promised. That's one side of it. I think the other side is also mindset, because the traditionally engineers and managers are used to the traditional manufacturing. They've invested their time. They are all kind of experts on the traditional manufacturing. And when you kind of bring this additive manufacturing, which completely eliminates lots of steps, how we manage a traditional manufacturing. So there is an acceptance challenge and mindset challenge too. So that's an awareness and capabilities. That's challenge that I was referring to. And then the last piece I will touch upon is the sourcing the right talent. Now, additive manufacturing, as I mentioned, is kind of a combination. You're looking for talent that is in the intersection of material science, manufacturing engineering, computer science, software engineering, and then your operations and mechanical engineering too. So you got these 5 or 6 disciplines, and you're looking at talent that is kind of overlaps, and at least a team that is kind of brings all these perspectives together to solve the problem. And that's not easily done. In fact, as I mentioned at the beginning of this series, there is going to be a premium for talent that understand digital side of business, all these digital technologies, and the traditional manufacturing and operation side. So the combination of that is going to be very, very much in demand, and that's a message for some of our learners. So that's actually the challenge here. I'm listing as a challenge, also as an opportunity if you're somebody seeking a career in manufacturing. Let's come to some of the sources of risks. Like additive manufacturing also comes with risk. There are some hidden risks, some explicit risks. Let's first start with cost. I mean, additive manufacturing, for all the promises, it may also have some hidden costs. Sometimes we talk about the time it takes to set up the printer, the time it takes to kind of work through different challenges that come to kind of finalize the product. They may be underestimated, right? I mean, the ease with which a material works on a particular printer. There are so many uncertainties. There could be some hidden costs. It's not like within a day or something like that you can finalize and then print it anywhere. That's not, for industrial production, it's not there. It is there for some consumer 3D printing, but it's not there for industrial. So there is a lot of, hidden costs that need to be considered as risks, potential risks. The next is cybersecurity. In additive manufacturing, as we know from the process that we are digitizing the design, all the design information is in digital files. And whenever we are in digital files, then of course it opens up, unless we take all the right precautions, it opens up to cybersecurity risks, right? There is a possibility of, hackers getting into the files, getting into the system and stealing files. All those possibilities are there. Those are risks that actually comes with, even in traditional manufacturing, we do have digital design files, but in additive manufacturing, it is much more integrated, and hence this risk should be kind of addressed, adequately. Then the next step is intellectual property. In some sense, this whole concept of combination of computer vision and additive manufacturing actually brings some new set of risks for manufacturers. Because these capabilities, what they do now, I can actually, if I have a part, I can actually kind of scan the part digitally, right? And then from scanning the part, I can extract information about the design of the part, and then I can actually go and use additive manufacturing to print it. So that can violate intellectual property, because there's a kind of a gray area. This has to be governed very well, because who owns these intellectual property rights, and because like manufacturers run the risk where they have parts that are printed, 3D printed through additive manufacturing. They have it in the field. Maybe somehow somebody gets hold of those parts, reverse engineers the parts, scans the part through 3D scanners, and then 3D prints another version of the part, right? And which actually kind of may not have the same design parameters, may not have the same performance parameters or quality parameters as the original part, and that can put the manufacturers in risk. So there is a risk that has to be thought through, and then see how that can be mitigated. And the last piece is about leadership and change management. As I referred to a couple of times, I think leadership is going to be key here. This is a new process, and it is kind of challenging the existing approach to manufacturing, and hence it has to be championed, it has to be nurtured, it has to be given that all the resources and the kind of the runway time that it needs for it to be launched as a successful experiment, and then given the momentum for it to be scaling.
So, John, given all that excitement, of course, with additive manufacturing or 3D printing, depending upon whom you talk to, right, there is a lot of positive excitement, or they call it as hype, right? I mean, there is a lot of challenge, and it's still not there. So, in that context, first, do you agree with that? Can you tell us why there is this two viewpoints? Number one. Number two, what are the risks and challenges that actually comes with additive manufacturing?
Yeah, definitely. The hype, the 3D printing hype cycle is one I am very familiar with, and I think it's Gardner that has the Gardner hype cycle, where it's the trough of disillusionment. I think we're in the trough of disillusionment right now, which is when it goes from being a just this magical solution to everything to at the end of the day, it's another manufacturing process, and it has advantages and disadvantages just like other manufacturing processes do. And so no, everyone is not going to have a 3D printer in their garage to produce a part when their Ford F-150 breaks, because that's just not going to happen. Yeah. And so, but there will be companies that take advantage of it to lower their spare parts inventory or to produce parts more in demand. So when that pickup breaks, the customer has better service and the lower cost. And so I think we're at this point where maybe some of the hype is receding, but that might not be a bad thing, and we're starting to see a lot of applications of additive in the background. And so in parts that you might not even know are 3D printed.
Right.
And so from a challenges standpoint, I think the first is I mentioned it earlier, but materials, ensuring that the additive material set that you're using has the performance that you need and functionality that you need for your part, but also especially for larger companies, you need to get this material qualified, and so that can be a hurdle for our customers, because there is a fixed cost to get a material qualified, and unless a material is qualified and approved by your company, you could design a part and get prototypes printed all day, but they're not going to allow you to produce it at scale. Excuse me. So that's materials is one. The second is quality control. There versus subtractive methods or molding methods where you'll have an error, or a quality issue that would be repeated, from a mold. If there's a nick in a mold or something, that is something you can pick up with some level of statistical, process control. Additive has a different set of, quality, a different set of parameters that you need to take account for and manage for. When you're fundamentally creating a part, from scratch, every time. And so, that is an area that, we at Fast Radius have invested deeply in, is our data collection and, process qualification. So we can ensure that we can produce repeatable parts, as our customers need them. So those are two of the real, I would say the large challenges. The third which is out there is, of course, is cost. Additive is the aperture of parts that make sense to 3D print from a business perspective, economics perspective, has increased 100x over the past couple of years, but it's still, very tiny compared to the overall, spectrum of manufactured parts in the world. And so, we will see that aperture continue to open, over the coming years as material costs continue to decrease. But that is still, a challenge, I would say, for many.
Great. Thanks, Ali. Just quick, for those insights, based on, is there any specific risks or challenges that you think they should be aware of? Any one of you? Yeah.
Sure. I'll maybe rattle off a couple, and then Dominic and Ron jump in. So first, I'd say is don't believe the hype. Be skeptical. There are literally dozens, if not hundreds, of different additive technologies out there. I think everyone promises the moon, and you really need to understand the technology. So there's an aspect of you have to go and see. You have to go meet the manufacturers. It's a manufacturing technology. You can't engineer it. You can't understand it by sitting on the other side of a computer. You have to go see the process, go meet the people, truly understand what is this capable of and what is this not. So bring some healthy skepticism of the promises that are out there, for sure. And then beyond that, your success is going to be almost entirely dependent on having some level of executive champion that's blocking and tackling, that's fighting for you, that's giving you the freedom of movement to go out there and explore. Because you may not have that killer app, that sticky app right out the gate. You need some time, you need some cover to go and find that. And an executive champion can afford you that through resources, through time, through a buy-in at a board of directors or whatever level is required to make sure that you get that freedom. So those would be the two things that come immediately to my mind. Ron, Dominic, jump in.
I would say the biggest risk that I've seen is really understanding your customer and your customer's expectations. Because industries that are users looking to buy parts from providers, like you said, small, medium-sized manufacturing firms, ultimately are very different, those industries. And that's why a lot of times I think we see it as less risky to have an existing automotive manufacturer adopt a new technology because they understand all the ins and outs and how to speak the same language of their customers. And it's just another way to make a part.
There are many impressive future trends in additive manufacturing, both from the point of view of the technology itself and also from the point of view of social and business implications that this technology can bring. First, let's look at some of these trends, right? First, serial production. As I mentioned, the additive manufacturing as a technology is in a stage that, where companies are using it for tools, for rapid prototyping. There is some serial production, but I believe in the future we'll see that expansion into serial production because because there is the technology is evolving in a way where the cost is coming down. It is much easier and widely available, and that will lead to more 3D printed parts. Additive manufacturing is a concept being used in serial production. FDM metal, or the fused deposition modeling, which is actually one of the techniques of 3D printing that we talked about, some of the techniques. I think that will become more popular, especially in metal. Right now, FDM is used in printing, parts in thermoplastics and other polymers. And now this particular technology is now widely available across many materials, and including metal, and is also becoming cheaper and easier to access. So we will probably in future see more adoption of this in the manufacturing context. Then we will also see a more hybrid manufacturing concept. What I mean by hybrid manufacturing is we have the traditional manufacturing, as we understand, and then we have the additive manufacturing, right? Then we'll see a combination of the two. In fact, we did see some of the examples, like if you recall in this course, we talked about General Motors using that for rapid prototyping. They were using one of those parts that actually kind of air intake into the cooling the brakes. That particular part is used for prototyping. So where you see is that they may use additive printing for prototyping, but they may not use it for serial production. So you'd see a combination of additive manufacturing and the traditional manufacturing coexisting and complementing each other to kind of, so that they work together for the bigger business benefit of the manufacturer. So it can actually, additive manufacturing can speed up the prototyping and the design stage of that particular part, but once the part is kind of finalized, they may go to the traditional manufacturing if they are producing it in millions for the cost advantage that we talked about. So there is more and more we'll see the coexistent complementing each other of traditional and the additive manufacturing techniques. Another trend that I think we'll see is the development and the discovery of new materials. They have different strengths, and also smart materials. I think in the material science world now we are thinking in terms of you can actually place sensors in materials. You can actually kind of not only sensors, you can also put logic in the sense that materials actually take that input, and there are some intelligence in the material to kind of adapt depending on the circumstances. You would see more of this, and you'll see unique applications. This is not for mass production, but this would be kind of experiments will start in terms of unique application of these materials in situations where they are warranted. We will also see high specialization of 3D printing usage in terms of, because especially whether it is human organs or any of these highly personalized requirement, then this will give opportunity for more co-creation, more partnership between manufacturers and the 3D printers and the kind of additive manufacturing ecosystem players to come together to solve these high specialization problems and come out with the product or part for that. I think the concept of generative design on cloud platform is another thing that is evolving. I think that is connected with additive manufacturing, but goes beyond additive manufacturing. To make it easier to understand, let me kind of simplify this. There is this concept called generative design. If you're interested in this topic, and then in additive manufacturing, 3D printing space, you should actually learn more about this topic. And this because this is the future of where design is going, where you are not actually going to kind of precisely define the parameters. Like for example, if you're now defining this, designing this particular box, you want to kind of define that. Well, I want kind of a reasonably thick box. I'm going to carry some marbles in this, and that's how you define the usage of this box. And then you give some design parameters for this box, and then they actually the traditional way they go and design this. But in the generative design, everything is kind of digital, right? In terms of what you do is the digital platform, which are often in the cloud platforms. What you could do is you could actually define the problem in a much higher way. You can say that almost define what am I going to be using this box for? You don't give any dimensions of any design specifications of how thick the box should be or what the material should be. You just give much broader design requirements, and then the mathematical algorithms actually, and the intelligence machine learning techniques would actually go and explore the design space and come back with the optimal design for that usage. So in other words, you are actually kind of not defining the requirements at that granular level. You're defining the problem, okay, in terms of what is the problem you're trying to solve and what is the usage it's going to be put to. And then for that usage, the design is maximized. And that's how the automated design comes in place. And then once the design is coming in place, then you can actually take it to the additive manufacturing process and get it 3D printed. I think this concept of generative design is now is starting. I think it's being experimented, and already we have some parts being experimented in this. So that's one of the future trends. Now, the last point about distributed printing capabilities. I already talked about this in what additive manufacturing could do. Now, this has geopolitical, socioeconomic implications as well in terms of future trends. I'm not saying that we are there yet, but there is potential here, because one of the reasons behind 3D printing being hyped is because it could fundamentally change the structure of the supply chain. For example, more recently now we are just kind of coming out of the global pandemic. And what the global pandemic has literally highlighted is a very, very big risk that all the manufacturers were sitting on. That in many cases, they might have actually kind of co-located a lot of their supplier base in one geographical location, right? And often, if you see why companies took that decision, is because outsourcing of manufacturing. because it is often led by, both quality and cost argument, primarily by cost argument, because if you go to East Asia, if you go to, Asia in manufacturing, the labor is cheaper, and hence you can have an opportunity to manufacture at a much cheaper cost, right? That was the logic behind what led to outsourcing. But if you go back to additive manufacturing, now we just talked about how it is actually reducing the manual intervention, right? The human intervention part is significantly reduced. Then that fundamentally raises the question, do you need to outsource manufacturing for labor cost arbitrage? You may not have to. So in other words, through distributed printing capabilities, what I'm arguing is in the future, there is a possibility for companies, if additive manufacturing kind of picks up and gets to the level of serial production, they may actually rethink the structure of the supply chains and ask the question, do we need to produce the parts in different countries as we are located right now? Or with this particular capability, should we rethink how our supply chain should be organized? So these are some of the trends I kind of outlined, what we can expect in additive manufacturing. It's a very, very exciting technology area. I'm sure this will we saw the market potential in some of the industry reports, and I'm very, very optimistic about what's possible here. Actually, there is a very interesting debate around the advances in 3D printing and additive manufacturing, which challenges the traditional manufacturing thinking, where often companies have tried to source parts or take manufacturing to places where they have the cheapest resources, with the best quality, and that, as you know, has kind of taken manufacturing more global, distributed. One school of thought or argument is that advances in additive manufacturing can actually kind of bring back some of the manufacturing to onshore. What do you think of that? Is additive manufacturing matured enough for that, or is it just projection being made by people?
That is definitely a possibility for additive, right? So when we talk about additive, you hear people talk about things like hyper-local manufacturing, where you can have smaller manufacturing facilities printing parts, but those printed parts are produced closer to the point of need. So that reduces, the reason that's people think that's economically viable is because it reduces things like storage and warehouses, which you're paying for over time, as well as shipping costs and customs and all these other things that happen when you ship parts across the world. Environment as well, right? You're using a lot of energy to get those parts from one place to another. So this idea of hyper-local manufacturing is an opportunity, if it comes to fruition, like a lot of people seem to think it will, where companies can onshore their manufacturing back to the places where those parts are finally going to be used. A lot of that depends on additive, the costs of additive coming down over time, the ability of additive to scale over time, things like that, again, we talked about earlier, I think are mostly just a matter of time. Those things will happen. And then it becomes whether we as a society decide to utilize additive in that way or not. Do we decide that it's worth, I have a global company. I make some cars in Europe. I make some cars in Asia. I make some cars in the US. Maybe I just print parts in each one of those localities using local help, to do that. And I think that's a completely plausible scenario for additive in the future, and something that we can maybe look forward to. We'll see.
Great, thank you. So is this then, let's talk about, I would like to hear about your views on the future of additive manufacturing in terms of where this is going. I would kind of parse that into two parts. One is tell us about the technology. Where is the technology going, right? I mean, in terms of capabilities. And the second piece is, I would put it in a way of economics of production, economics of distribution as well, because now we can think about distributed production, right? I mean, we don't have to kind of, outsource production. Primarily, manufacturing was outsourced for cost arbitrage, correct? I mean, labor cost arbitrage. Now, is additive changing that significantly? So, two parts of the question. One, where is technology going in terms of 3D printing in the next 3 to 5 years? And second, what are the business implications, both micro at a firm level and a macro at economy level too?
Yeah. Okay. Great. So overall, I would say, I would say this with excitement, which is I think the hype train is over, and 3D printing is just becoming it is another arrow, in the quiver of manufacturing technologies that engineers have to bring their products, to life and to market. And so, and for me, that's a good thing, because that means it is now, being accepted as not just some kind of curiosity or something that's interesting or something maybe just for extremely high-end parts or, high-end companies or, but it's just another manufacturing process. And so, for me, the technology front, I see, I would see there continue to be advances in automation around the workflow, of taking a part and getting it to be, printable. And so there's a lot of investments, in the, what I call, like, from a more traditional standpoint, like CAD and CAM, but the analog for, 3D printing, that part of the workflow, there's a lot of investment in that part of the workflow right now. And Topology is a startup based in New York. We work closely with. There's a few others on the West Coast, that are building out software, really specific for designing and then making parts on additive. And so I think there's going to be that is going to drive a larger user base, of people that know how to use this technology, because it's lowered the barriers to production. So I think that's one. I think the second is, I really do believe, that on the metal side, there will be more innovation that will drive the cost down and increase the aperture on parts that make sense to produce with metals. And so, binder jetting is one where, it has been restricted to smaller parts. I am very bullish on, the size of that part, parts for that going from, a grape or golf ball type size to, maybe more baseball or softball type size. So I think that's a big thing as we think about the technology front. And then the last thing on technology is materials technology. So I think we're going to see continued innovation on the materials front. For example, I just spoke with a company a couple of weeks ago that has developed a ceramic-based polymer that you can 3D print injection molding tools with. So you can now, drastically lower the cost of your tooling. You can basically get a tool, in 10 hours, and you can do that in a way that's pretty highly automated. And so that really reduces. You think about your lead time for a low run injection molding tool. And so I think it's kind of software, materials, manufacturing platform and materials. I think there's going to be a lot of advancements in all of those areas on the technology front. As you think about economics of production, I do believe that companies that will embrace, additive, much like other, again, I would say much like other technologies, and other manufacturing technologies, companies that have been, in the forefront of embracing new manufacturing technologies, have proven out to be winners. And so I think, companies that do embrace additive and understand how they can use it to create products that will drive, consumer surplus, compared to existing products. I do believe that those companies will come out ahead. And, from a more macroeconomic perspective, in a world where, additive enables, more on-demand production, as well as, the capital required to start producing with additive is not as high as other manufacturing processes. So you can now justify, smaller size factories. And so, in a world where additive enables more on-demand, more localized production, I would see, I personally am excited for, for more localized production, here in the U.S. or in other geographic regions, local to the demand.
So the pendulum will starting to swing there in terms of more insourcing and production locally being done here. Is that right?
We've already seen it, I would say in the past 6 to 12 months, especially with the COVID supply chain disruptions. We've seen a very large uptick in customers, looking for more local options.
John, I was reading about your company. One example that is fascinating me was the partnership UPS is kind of making with your company, and I think it looked like they're making use of your concept of warehouse on the cloud or virtual warehouse kind of a model. So tell us a little bit more about it. So are we thinking about the possibility of UPS not really shipping physically parts from plant A to shop B or whatever it is, but just coming to companies like yours and say, you know what, here is a product, deliver one to me in Chicago, in this particular location. Is that what is happening here?
Yeah, so UPS is an investor in Fast Radius and a partner, and the long-term strategy is, in a world where new manufacturing technologies enable more localized production, there's less of a need for shipping parts long distances, and so part of our strategy with UPS is to co-locate manufacturing facilities on their hubs. So we have one at their Worldport hub in Louisville that enables, very quick turnaround, I'd say localized production, but also quick turnaround. And so, our strategy is, to roll out, a manufacturing network in conjunction with UPS's footprint to deliver, more localized on-demand production.
Ashley, I would like to hear from you in terms of the future trends in additive manufacturing. It's pretty impressive in terms of how it is just a concept, an idea 10 years back, but the rapid, progress that we have seen in additive manufacturing and wide set of industries being used. But, starting from here, what do you see in the next 3 to 5 years, and what implication does it have for manufacturing?
Well, let's talk about the 3 to 5 years, and then I'll give you some that I think are even further out that we can talk about as well. So 3 to 5 years, we're going to see an evolution of the technology as it stands today, right? We're going to see things like the costs come down, the number of materials available go up, the number of processes that companies use, the techniques they use for printing these things, those are going to multiply, right? We're also going to see a lot of consolidation. So this is an area where I go to these trade shows and there are literally hundreds of printer manufacturers. And we're going to see people with unique ideas kind of start to consolidate. Some of the big fish are going to buy some of these technologies from the smaller companies and start integrating them in. So we'll see a lot of that over the next 3 to 5 years, right? Sort of variations on the theme as additive matures as a technology. You get beyond that, we get to some really interesting things like what we call digital materials. So one of the interesting things about additive is that because you can place material at a specific spot in 3D space, it gives you the opportunity to make parts that behave in ways a normal machined or injection molded part wouldn't. So for example, if you have something like a spring, right? A spring is something that allows you to absorb energy and return energy. Well, you can manufacture springs or energy absorption and returning structures inside of parts now with additive, because you can put that material exactly where you need it. So it allows you to do things like have parts that act as heat sinks, thermal transfer. So again, we're talking earlier about like electric vehicle batteries. They have these huge heat sinks on them because they need to be able to dissipate the heat when they're being charged. Well, you can print structures that are much, much more efficient at dissipating heat. And those structures can also be, they can handle compression and expansion as the vehicle moves, right? So you can start to combine functions of parts, and things that would have normally been done either using multiple parts or multiple materials can now be printed into a single part. And so as people understand the underlying physics of these materials and the way they behave after they're printed, you're going to see a lot more of these applications come on board that allow you to do truly amazing things with this technology that, some of which I'm sure we can't even envision at this point. It's going to be awesome.
What I'm understanding is you're saying because of this capability, we can even now print intelligent products, right? Which is kind of sensing something, taking in information, and saying, responding based on the fact that we can actually print these designs inside the product.
Yeah, I've also seen, these are research projects, but things like printing sensors inside of parts as well. So if you have like a bearing on an aircraft, the bearing can be reporting back to you its health as it's used out in the field, and it will let you know when it's about to break. So you don't have to do these cycles of repair, well, it has 10,000 hours on it, it's time to take it out. Well, if it's still good, why, that's a waste. So you can wait until the bearing tells you that it needs to be taken out. Those are the sorts of things that will become possible. And like I said, it's going to be awesome.
Great. Thanks, Ali. Ron, actually, I would move that same question from the context of, Michigan, as we know, has been the manufacturing hub of the country for almost, a century now. So and Michigan manufacturers, all the OEMs, they are used to the traditional manufacturing ways. So how's this ecosystem developing in a broader Michigan context with all the, big auto OEMs here?
Yeah, thanks for your question. And first of all, my compliments to you on this format and the gems that you're giving your students through this format.
Oh, thank you.
As a student at Kettering, maybe a school at Flint, I had a professor there that also brought in industry experts, and I still to this day, 30 years later, remember their advices and their thoughts on what the future held. And it formed strong opinions with me about what we ought to focus on as leaders when you had the chance. So it's a great format, and hope to continue that with you.
Thank you.
It's an interesting question about Michigan as the hub. I tell you from the position that we think about it, we also think about it from an industrial perspective on a global basis, right? So from a China policy standpoint, 3D printing, additive manufacturing is a policy commitment to develop and to dominate the space by 2030. And you see major installations in China where somebody will go out and buy 30 and 40 metal printers. And I'm not going to talk about where that funding comes from and this and that. It's planned a different way, but to lay that on the heels of our entrepreneurs and inventors in the States, right, anywhere in the United States, not just Michigan, is a tremendous challenge because right now, at least, these printers are $2 or $3 million, and the know-how that goes with it. Ali's talked about the software, the ecosystem to put a plant together, as Dominic knows, is no easy adventure. We at General Motors just started a $25 million facility over the last year. So we have those firsthand experiences and challenges. Insofar as Michigan goes, when we traveled the world to see printers, different companies, different universities. And I would tell you the state of Michigan needs an additive manufacturing policy. It needs a policy that extends all the way to university. Let me be very specific because, Professor, you know me by now. I'm pretty straightforward.
Yeah.
When my daughter went to Michigan, she was roommates with a student who worked as a marine engineer. And there was no finer facility, I guess, in the United States than marine engineering at Michigan, right? When I think about your counterpart up north in Lansing, we won't name the school, but we talk about them very often as having a phenomenal packaging program, right? And so if I was to talk about where in Michigan is the additive manufacturing hub of education, I can't name where that is today, right? So we've got an opportunity. And courses like yours help us get to that place that we want to be. Most recently, though, we've got some initiatives from Automation Alley. Automation Alley is a soul of the I-75, I-96 corridor to coordinate industry and business practices. And there's individuals that are interested in this hub and spoke idea of if we ever had another need during COVID, to wake up 1,000 printers to print things like Dominic Lin team did to make nests for masks, that this cooperative kind of activity could be brought together in a network. Again, and you talked about it early in your presentation, the hype versus the reality of that. We're well aware of the software challenges, the desire to work in cloud computing versus the security that General Motors tries to work with. And so a lot of things we do in automotive are descendants of the military, descendants of aerospace, descendants of medical products, right? Where the value proposition has been more attractive than the hyper competitiveness of automotive, where we talk about tenths of cents, not dollars.
To summarize, let's go back and look at the learning objectives we started this course with. So we first looked at understanding what this technology is about, and we compared this with the traditional subtractive manufacturing and understood how additive manufacturing is different and what kind of benefits it brings to the manufacturer. Then we looked at specific manufacturing applications, right? I mean, not just in terms of ability to print, 3D print, but specific cases where additive manufacturing is able to consolidate parts or kind of reduce weight. We saw specific applications from different industries. We looked at a couple of examples first. Then we looked into multiple industries who have the right criteria that is required for additive manufacturing. We then understood the economic trade-offs in additive manufacturing. We carved out the business advantages in terms of productivity, quality, cycle time, customer engagement, and also the most importantly in additive manufacturing, the sustainability part, right? How additive manufacturing optimizes the consumption of materials and hence may actually kind of make the manufacturing plants more greener and the business more sustainable from an environmental perspective. We then looked at additive manufacturing as a new technology, which also kind of brings kind of implementation challenges. We talked about how organizations should prepare to make this a success. How should they build additive manufacturing capabilities inside their organization? Not only that, how it is important for them to build the ecosystem of additive manufacturing, working with internal and external partners. Then with any other technology, of course, this technology also comes with risks and challenges. We explicitly address some of these challenges and risks and that this technology comes with, and also ways to mitigate those risks. And finally, we discuss some of the future trends and what are the potential for this technology. And it could not just about technology aspects of it, but both socio-political and business aspects of this technology in terms of what we can expect in future trends. Now that we are on the conclusion of this series, let's go back and revisit how we started and some of the technology trends we talked about. We talked about how digitization has evolved in manufacturing industry. Let's go back, revisit, and see what we learned in this course or in this series actually connects with those trends. If you recall, I started saying that, since 2015 or so, we call something called as Industry 4.0. Before that, it was Industry 3.0. And that is because of the new digital technologies that are coming into the manufacturing world. I also told you that, automation and technology usage in manufacturing is not new. Robotics has been in manufacturing for many years. We talked about digitization of processes in manufacturing in various ways, whether it is computer-aided design, product lifecycle management, or ERP. We talked about these have been existing for decades. And then we also touched upon, the programmable logic controllers, which allows the flexibility for manufacturers. And this has been there for quite some time too. But in this series, we started talking about some of the new technologies that we're going to be learning. And so let's go and see what did we learn in this series. Well, we covered specifically 3 technologies: the Industrial Internet of Things, which is IIoT, your digital twins, and additive manufacturing. In each of these technologies, we went through a framework to understand what these technologies are and how do they work from a simple layperson's standpoint. And then we kind of understood how to apply these, how they are applied in manufacturing context. And we went to look at practical examples, discussion with our industry experts who kind of brought in the relevance of this technology and how they are using it in their context. And then we understood through a framework the various dimensions through which companies can get business value from the application of these technologies. Then we moved on to understand the broader ecosystem of different players who actually kind of enable these technologies, and more importantly, for our learners to understand how do we build these capabilities, and what are the different layers of both technology and business decisions that lead to these capabilities. Then we spend a lot of time understanding the implementation framework. While you may have a technology that works, how do you make it work successfully in a project within the organization? So we talked about the entire implementation framework. And finally, we understood the challenges and risks that comes with these technologies. And then we also spent some time discussing the future trends of these technologies. Now, let's go back to the digital trends, broader digital trends we talked about when starting this series, and see, broadly how these technologies relate to those. You may recall I talked about the Hexatech disruptive trends, right? The 6 technology trends, as you see in this chart. Now let's go one by one and connect this to the technologies that we learned in this series. Ubiquitous connectivity. Industrial Internet of Things, or IIoT, and digital twins, as we understand it, they actually build on this connectivity framework, right? Now, the ubiquitous connectivity is not just about connectivity across people, it is also connectivity among things and objects. And basically, we are embedding intelligence into these objects and connecting that to the network and with people, and that's what these technologies are. Next, pervasive digitization. Of course, IIoT and digital twins we're all about digitization of the processes, right, where we can actually put embedded intelligence and then, change the business process of decision-making process based on real-time information. But when it comes to additive manufacturing or 3D printing, we saw that we can actually digitally capture the structure, the properties of that manufactured part. And you could also simulate and explore multiple options to improve the design. So we talked about in detail what are the possibilities there. The next technology trend we talked about was cloud computing. If you recall, in one of the courses, I spent some time on cloud computing explaining what it is, because that's an important trend, technology trend, that is, in fact, making the possibilities of usage of the 3 technologies we covered in this course, IIoT, digital twin, and additive manufacturing, in several new ways, delivering value to the manufacturers in different levels. For example, the cloud platform allows manufacturers to scale any of these technology capabilities. You may recall our industry experts refer to hyper-cloud platforms like AWS or Microsoft Azure. That's how some of these technology, IIoT or digital twins, technology platforms are hosted. That's because if they have a successful implementation in one place, they can easily scale it across different plants. The second important aspect of cloud computing is that it democratizes the access to these capabilities that we talked about in these technologies. For example, if you have an IIoT or a digital twins platform, now once it is on cloud, then it is also not available only to the large manufacturers with deep pocket with a lot of heavy investment that they can make, but these services can also be rendered to small and medium manufacturers. And that is a profound implication for the manufacturing ecosystem and the opportunities that are opened up for smaller manufacturers as well. Of course, all these three technologies we talked about depend heavily on data analytics and the intelligence that comes through data analytics. For example, we talked about the role of artificial intelligence and machine learning in the applications of digital twins in making proactive decisions, or even in additive manufacturing where you explore a design space to come out with the optimal design. We talked about social networks, but social networks is a kind of more business to consumer concept. While we did not directly address this piece in any of these technologies, but if you think about when we talked about additive manufacturing, the ability of manufacturers to personalize the experience either in the product or in the case of process in digital twins, and that actually kind of relies heavily on the personalized demand coming from all these customers, and that is in a way influenced by the social network of people or the customers or consumers connecting with one another on these networks. And last but not the least, we've talked about smart sensor networks. I often use the term embedded intelligence. IIoT or digital twins is nothing else but you putting intelligence in both products and processes, through sensors and different other means, and those sensors are powered by machine learning algorithms. Now, coming to additive manufacturing, we also talked about in the future trends of almost intelligent materials, right? Where we are able to kind of put sensors in materials where the materials can actually kind of behave differently depending upon different context. So that in a way sums up how the three technologies that we talked about connect with the broader digital trends, disruptive trends that we introduced at the beginning of the series. If you recall, I also talked about the digital transformation of how we manage in the manufacturing operations, right? If you recall this chart, I was talking about why in Industry 3.0, or maybe 10 years back, a lot of focus in automation was about unit level automation and monitoring at the unit level and optimizing at the unit level. I promised you that these digital technologies that I'm going to talk about is going to bring capabilities for what I would call as end-to-end visibility, end-to-end orchestration of how a manufacturing operation is working, so that managers can control this. Looking at sitting in a control room, or often called as war rooms, where they are looking at cloud-connected technologies, which enables them to have real-time visibility to the operations. And that's exactly what we saw in the applications of, if you recall, the IIoT course, for example, a simple cloud-based platform that allows, embedding of sensors and intelligence to connect with as simple as an RFID sensor to robots and industrial machines in manufacturing operations, to individual managers and workers working with their handheld devices, or to logistics operations outside. So this integration of all these operations through sensors and on a common platform starts to bring that that capability we talked about of a single control room from which you can see the entire operation. This further we discussed, as based on the platforms of IIoT. When we moved to digital twins, you recall we talked about that we could do digital twin at a part of a machine, or we could do digital twin at a machine level, or we could do digital twin of the entire manufacturing operations, where you can actually kind of digitally view the operations of each of the machines in the shop floor, and you can monitor that real time, sitting in one control room. And also with the cloud-based platform, you can monitor that from a remote location as well. We also talked about the fact that the future of manufacturing would kind of look probably different from what it was in the pre-2015 era, where a lot of focus was on unit level optimization. We focused a lot on lean process management, continuous improvement, things like that. And I told you that the new trends are about embedded intelligence in product and processes that we saw in digital twins and in IIoT. We talked about integrated technologies in cloud platform. I already talked about that. And of course, we also said actionable insights using real-time data through human and machine intelligence, right? And then we referred to reimagining the process. It is not about taking a process and automating that process, but reimagining the process. If you recall the example of digital twins and the propeller, right? You have an option. You can just digital twin of a static propeller that you can just have static information, static digital image of the propeller, and that's useful sometimes. But we talked about you could also go to the full extent of dynamic digital twin of the propeller, where you have sensors and it is creating and is collecting real-time data and feedback and providing the feedback of that real-time information back to the central location so that you can take real-time decision based on analytics on this real-time data. Now, similarly, we talked about the application of the combination of human and machine intelligence when we test autonomous vehicles. And this is a concept of digital twins. In our course, we give this example where we said when testing autonomous vehicles, you often see, you have a vehicle test track, and when you're in the test track, you may have a physical vehicle, you may have a virtual vehicle, you may have a digital twin of a real vehicle, or you can have a purely virtual vehicle which is being operated by machine intelligence, and you put that in combination with human intelligence of somebody driving the vehicle in the test track, and that's how you get, you're able to simulate the entire scenario where you want to test this autonomous driving capability. So that's an example in digital twins of combining your human intelligence and machine intelligence. Let's revisit the consumer-driven change in manufacturing that I introduced at the beginning of this series. Let's see how the three technologies that we talked about connect with some of these consumer-driven change. You may recall we talked about these consumer-driven changes, and in fact, if you also recall some of our industry experts when they were talking about the changes that are happening in the manufacturing industry, they highlighted that there is a big change that is coming from the consumer side, right? That we talked about the demand for more personalized N equal to 1, sample size of 1, personalized hyper-personalization and personalized experience. We talked about real-time engagement and proactive solutions. Of course, the examples of digital twin and IIoT, we just talked about, showed us how we are kind of moving to more real-time engagement. And we also talked about evolving product features and new business models. Now, let's kind of connect to a couple of these. Let's recall our discussion about additive manufacturing. You may recall this chart where we presented the economic trade-off of traditional manufacturing versus additive manufacturing. In the traditional manufacturing, you cannot do lot size of 1 because the economies of scale is what the entire model is dependent upon. You have to have a reasonably bigger lot size so that you're able to get the cost reduced. However, in additive manufacturing, as we know, the way it works, you're actually printing one part at a time, and anyway the design information is captured digitally. So in case if you want to personalize and print a part for each customer, then it becomes much easier in additive manufacturing. So in other words, additive manufacturing is in a way helping manufacturers move towards the possibility of lot size of 1 or hyper-personalization. You may also recall that in the last bullet point about new business models that I have here, in one of the project examples in the digital twin course and also in the IIoT course, you went through an experience where the combination of these technological capabilities can even shift the business model of these manufacturers. In some cases, the deployment of digital twins and IIoT applications can help the managers deeply understand the customer engagement, and in some cases can even move from product selling business to selling of experiences, so that the customers are charged based on usage of the product, not just in terms of one-time selling of the product. That's the change in the business models. We also talked about the organizational challenges in digital transformation, because we referred to how these digital transformation with these technologies, kind of will lead to new business processes, new understanding of technology architecture, probably changing the technology architecture, and we talked about skills and talent and broader organizational culture as well. Now, if you recall from some of the examples that we talked about in IIoT, digital twins, or additive manufacturing courses, we saw that the first, fundamentally, these technologies allow manufacturers to reimagine their products and processes. So we introduced this technology implementation framework where step by step we took all the organizations through how they should ensure that there is a success behind the attempts to kind of implement these technologies, because these technologies are complex, and they cannot underestimate this complexity, because often some organizations fail because they have not taken into account all these challenges that may come, and also how do you proactively build some of these capabilities. If you recall this framework, we highlighted in the first step about the importance of identifying the right prototype or the right initial project to make it a success initially, and then we talked about building capabilities. We focused on building center for excellence and building the right talent pool. If you recall, we emphasized that the talent that is required to successfully implement these technologies are going to be multifaceted. They're going to be from multiple disciplines. Whether it is the combination of computer science, operations knowledge, digital skills. And in the case of additive manufacturing, if you recall, I talked to you about the intersection of skills coming from manufacturing, engineering, and mechanical engineering, and operations, material science, and computer science. All these things come together to kind of successfully deploy that technology. Then we talked about the importance of leadership and sponsorship, right? An executive sponsor has to be behind these technologies for them to work. We talked about aligning and partnering with both internal and external partners, and for learners to understand who are the main players, how does this technology as a capability evolve inside the organization, and finally we focused on execution. In summary, these technologies basically are kind of allowing the managers to completely rethink how they compete, how they design their products or processes, and also how they put their teams together with the right skills and talent. Bethany and Tavia, I was just thinking, maybe since Siemens is in a very interesting position in this digital transformation of manufacturing, because you guys are providing the platform for other companies to, transform themselves digitally in their manufacturing, right? And you work with, hundreds and thousands of customers. Your platforms are so ubiquitous in the manufacturing context, especially in the smart manufacturing and digitization. So I thought I'll ask you, is there anything that you've seen across your customers in terms of how they have taken, how they've approached DEI in the context of the digital transformation that basically, that sticks in your mind? You said where you found you're very impressed with what they're doing, and something that you can share with our learners.
So one that comes to my mind is actually from a partner of ours. Siemens has a strong partnership with Microsoft, and Microsoft has been working very hard and openly in the DE&I space for quite a while. And for the past couple of years, they have held a conference called Include, and Include 2021 was virtual. It was just a couple months ago. And I believe you can still find a lot of the materials online. But what struck me, I attended it, and what struck me was that throughout the conference, they had vignettes from Microsoft employees where the employees were telling their true, authentic, genuine stories of themselves, and really seemed to hold back no detail. And you could tell we're very much encouraged to be their authentic, genuine, whole self. And to me, that signaled a level of inclusion and diversity, of course, and equity that Microsoft must have in their organization, that is not only just saying we have it, but there are employees who are standing up and saying, allow me to be a representative of this. Please allow me to be an advocate and a spokesperson for the importance and the value and the benefit of diversity, inclusion, and equity in the workplace. And it struck me because I just had to wonder how many organizations are at that place today where they would truly have employees raising their hand and saying, please let me tell my story and why I belong here in this company.
So what are the business implications of the three technologies that we covered in the series, IIoT, digital twin, and additive manufacturing? If you recall, we have a framework to kind of extract and understand every dimension of the business value that comes from each of these technologies, right? If you recall this framework, we talked about productivity benefits and cost and efficiency benefits of each of these technologies. Then we went on to quality, how the sometimes just the quality process is improved, or sometimes even the quality process is redefined. And we talked about the cycle time benefits, at the individual business unit level, end-to-end manufacturing cycle time. We looked at those, and then we also saw specific examples of how these technologies could enable manufacturers to become more safer and make it easier for them to comply with the requirements of regulation and so on and so forth, right? I mean, if you specifically recall some of the examples our industry experts were sharing, and they related to, these technologies not only give you cost and quality benefits, but they also make both the manufacturer as an organization and the individual employees safer. And finally, the last not the least, we talked about the customer experience and sustainability. There are two pieces there, right? We talked about how, because of the manufacturers using this technology, leads to a much better customer experience, because now there is a real-time engagement between the customer and the manufacturer. The customers can now expect proactive solutions. Say, for example, if a manufacturer is using digital twins as a capability, they can then proactively detect a problem before the customer is going to experience it, and that could be addressed. That's one example, just from digital twins. And similar examples we can give from the other two technologies as well. And then sustainability. We spent a lot of time talking about the sustainability benefits of these technologies. All these three technologies actually lead to reduction in wastage of resources, improvement in efficiency, so hence the broader improvement in the carbon footprint of these manufacturers. Specifically in additive manufacturing, we talked about how in some cases it completely transforms the whole approach to understanding producing a part, and how much of wastage is basically saved as compared to the traditional approach of manufacturing, which is we call the subtractive manufacturing. And just the reduction in resources, reduction in the number of parts, combining multiple parts into one part, and enormous resources are saved, and hence lead to sustainability, both in terms of reduction in wastage, and also technologies like 3D printing leads us to look for materials which are actually more sustainable than traditionally what we've used. So that sums up how we understand the business value of these technologies in multiple dimensions. So finally, let's come to the social implications. I think one of the most important aspect of digital transformation of manufacturing. Well, a recent report shows that the number of job openings in manufacturing industry is growing significantly. In fact, the data stated here is the open positions in manufacturing has risen from less than 100,000 10 years ago to more than 350,000 in 2019. Well, that means there are 350,000 jobs that are open, and the positions that are not filled. The industry wants them, and we don't find people. In some sense, this is a talent gap. There is a demand for opportunities. There is a demand for jobs, but they're open right now, right? Well, let's see why. This recent survey from World Economic Forum and McKinsey, identifies some of the top skills that are required in manufacturing today are the following, right? You can see the skills here: data analytics, technical equipment, or digital tools. I mean, predominantly all these skills are connected to digital technology and digital skills that we talked about in this course. Now, in fact, I would say that there are only 3 of the skills here: problem solving, communication, collaboration, change management, and probably quality are the only 3 skills that stand out, which were seen as, manufacturing talent skills as in the traditional manufacturing, right? And before Industry 4.0. The fact that 350,000 jobs are open and these are the skills that are required actually tells us that there is a gap between the talent that is available and the skills that are required, right? And then so it's kind of, there is this gap and manufacturers need to understand. In fact, manufacturers need to understand that the digital transformation of manufacturing is leading to 2 outcomes. First, it is creating demand for new roles. As we just saw, so many jobs open, right? If you have the right skills and, as listed, in the previous slide, then there's so many jobs that are open. So it's basically creation of new roles, creation of new jobs. So at the same time, what you see in the bottom is when you reimagine the business process or reimagine the product, as we talked about in this course, then it could also be leading to elimination of some of the current roles, right? If the entire plant is being, for example, monitored remotely in a control room, right? That may probably reduce the need for the same number of supervisors as every cell, right? I mean, that we used to have traditionally. That's one example. The point I want to make here is manufacturers need to understand that this dynamics of there is demand for new skills, there's a lot of opportunities, and at the same time, there's a challenge of elimination of the current roles, and hence they need to deal with it in terms of and come out with strategies and policies of how they're going to take their current employees, reskill them, upskill them, to the extent possible, make them prepared for the new jobs that are coming, new roles that are opening up. So that is a dynamic that manufacturers have to deal with. There is a broader social implication that comes out of the digital transformation of manufacturing industry. We talked about enormous business benefits that accrue to manufacturers or the convenience that comes to consumers from this transformation. However, we need to ponder, are the dividends that are coming out of this transformation, are they being equitably distributed across the society? Do we have diversity in the people who are working in this industry once we see the digital transformation of manufacturing? Well, some of the data that we see now is makes us ponder. For example, one of the recent reports from OECD shows the underrepresentation of women in digital intensive industries. And second, as you can see, there is a recent report from the Brookings Institution which shows that while blacks make up 11.9% of all workers, but they only represent 7.9% of computer and mathematical skilled workers, which is the digital transformation jobs that we're talking about, right? And similarly, the gap is even larger for Hispanics, who make for 16.7% of all workers, but only 6.8% of computer and math workers. So this goes to the point that we have to. It is as a society we have a responsibility that these corrections are made because and there is diversity and equity and inclusion as we manage this digital transformation of manufacturing industry. I believe that to ensure diversity, equity, and inclusion in this digital transformation of manufacturing is a collective social responsibility. In fact, I see there is a role for manufacturers, there is a role for technology companies, and also there is a role for education institutions. Starting with manufacturers, I think it is important for them to understand the nature of this change, understand their current worker base and what their skills are, and where the skill gaps are, and how do they upskill or find different new roles for their current employees. Similarly, tech companies have an obligation to kind of work with the manufacturers and educational institutions so that they can both train current employees, but also prepare our younger talent, the new talent coming on board in the industry, that they are made aware of all these technologies and these opportunities, and they can prepare adequately. Education institutions, I think, need to work with manufacturers in probably new ways, because the rate at which these technologies are moving, it is very difficult for education institutions on their own to catch up with the industrial application of these technologies. So I believe that it is going to lead to new approaches for manufacturers to collaborate with education institutions, so that not just theoretical understanding and exposure to these technologies, but also co-create learning experiences for students and their employees working together on practical aspects of applying these technologies on real projects. So in other words, I think what we are looking here is a collective responsibility for all the stakeholders here to make it as a lifelong learning journey for a diverse set of population, so that we make sure that the digital dividend that comes out of this transformation is equitably distributed, and it is collectively win-win for all. At the end, I would also emphasize that the responsibility lies also with individual learners. I think individual learners have to recognize the importance of this technology trend that we are seeing and this profound transformation that is happening to this industry. If the learners are interested in building careers in manufacturing, they have to invest time in understanding these technology trends and how it is shaping manufacturing. And it cannot be about just doing one course or getting one degree from an institution. And this is a lifelong learning process. They should be prepared to invest in themselves and invest time to learn this trend. Finally, I would like to thank all of you for your engagement in this series, and I wish you all the best.
Ron, I would actually now, look to you for, given your rich experience in manufacturing. First, I know you mentioned earlier about, noisy, dirty manufacturing. That's what manufacturing was all about. And whereas digital technology is fundamentally transforming as we understood manufacturing, right? So first, from the context of this transformation, right, what will be your advice to our learners, right, and who are either our students or who are currently in the manufacturing industry and looking to kind of advance their careers in manufacturing? And so in this new manufacturing that is evolving, what will be your advice to our learners?
Yeah, so that's a great question. And part of it, Ali and Dominic already answered in terms of go see.
Mm-hmm.
Genchi Gambutsu, right? Go and see the place where work is done.
Mm-hmm.
So that rich experience includes time at NUMMI with Toyota, when GM had the joint venture with Toyota at NUMMI. And we're taught that you have to get out from behind your computer, that the reels on the factory floor are what determine your success or failure. In that context, right, you can go to a show. There's a show coming up in Chicago, the Rapid show that talks all about additive manufacturing, right? That's where you're going to get a lot of hype. Okay. And then, like at U of M, you have a footprint, if you will, in the additive manufacturing labs, where students are hands-on, they're touching, right? And I say dirty, noisy, smelly in the context that that's where you learn. Go see. We spent, as Dominic said, we spent a lot of time, 2 years, in fact, going around the world to see all the manufacturers, meet the people behind the technology. What were they thinking? Scott Crump at Stratasys was thinking about making a new green frog for his daughter, and it started with a glue gun. And today they call the business Stratasys, and it was the precursor to FDM printing. To hear Scott tell the story, right? To hear the stories behind EOS, to hear the stories behind where the materials are coming from.
Yeah.
It tells you where they're thinking, right? And it isn't something you're going to sit and mine by looking on the internet. You have to go see, you have to go to the operations, and you have to do another thing. And that's somebody gave us 2 ears and 1 mouth.
That's right.
The students for a very long time in their career should follow the advice of their creator, whoever created these ears, to listen and to learn and not tell them what they think, but to spend a lot of time. As I have the greatest respect for Dominic and Ali because they live this every day. They're very smart academically from Michigan and MIT, but they're always learning and they're always listening. And I hope your students adopt that as a modality, especially for the first 10 years of their life, where so many of them want to start to become entrepreneurs.
That's right.
Be the boss right away. Yeah. Again, I say it's a great responsibility to lead people and to lead them the right way. And you have to earn that by knowing what you're talking about. And having launched a lot of different technologies and things, you see trends. And Dominic talked about it in the context of winning hearts and minds.
Yeah.
Ali's got hands-on experience trying to get different designers to think different. It's a responsibility is what I'd like your students to understand, more than anything, a responsibility.
Tavia, you have a rich experience, as a human resources executive, and you've seen the talent pipeline coming into Siemens and other organizations who are undergoing this digital transformation. So what would be your message to our students, who are college, in the college or universities, and that's part of our persona in learning here. What would be your message in terms of how do they prepare themselves if they have interest in, career in manufacturing?
So, to prepare yourself in this industry, familiarize yourself with something very elementary: STEM, science, technology, engineering, math. It's starting to, it's a term that has been targeted to young children and to high school children. But if you are a business major, let's say, and you still want to be part of this wave of digital manufacturing and you see this trend, familiarize yourself with simply STEM. And what does that mean? STEM tells you exactly the direction by which the world is moving and how those entities are so important, even if you're a business major or a marketing major, because you need to understand not intimately or intricately what technology is or does, but to have a healthy understanding of how math, engineering, technology, science plays a part in every aspect of our lives. We are now being moved by science and technology. At one point, it was a very separate entity from business. If I was a business major, I didn't need to understand math, but that is no longer the case. Familiarize yourself with those basic 4 entities of the wave of how products come to market, and you will be able to easily transition into a company such as Siemens or any other software company, because the details of engineering, although are still very important to us, and we are still definitely want engineers as employees, we also need someone to understand the, again, life cycle and the overall reach of a product and how what we do is going to fit and assist our customers in getting those products to market, creating marketing tools so that they can continue to improve that product. And if you understand how math, science, and technology fits into your business model, you still will be able to be successful. So open up to those entities: math, science, technology, engineering. The STEM side, find it anywhere, look for those, start that very elementary understanding of those four entities, and then leverage your business and marketing knowledge to incorporate those into your knowledge, and then still walk into a company like Siemens and say, hey, I can still run your company because I understand what an engineer goes through or what a technologist goes through.
Great.
Thanks
For that perspective from HR. And I want to switch to Bethany. You are in strategy and marketing. You are managing these customer engagements and projects. So as Tivia mentioned, our students are a mixed group, right? I mean, we have engineers, we have business majors, we have kind of liberal arts. One way to look at the way I see this transformation that is happening in manufacturing is no matter which thread they come through, right? I mean, this is reality in terms of how manufacturing is being transformed. So, what will be your advice based on your experience?
Well, my experience is the experience that you are referring to is also my personal experience. So I was a communications and public relations student. I've had a career in marketing in a few different industries, but never industrial manufacturing. So when I got the opportunity to work at Siemens and specifically Siemens software, I jumped at it without thinking first about, do I really understand the technology of what I'm going to market? So I've been there. I've lived it. What I have come to learn is that before anything is about the technology or software, it's about the people. Yeah. And from a business perspective, it's either about it should, number one, be about our customers, but we also know it needs to be about our shareholders as well. Yeah. And those are all people. And like I said in the beginning, we really, if we're doing anything that has to do with the human beings and the people that make up the success of an organization, we can't do it without the intention of diversity, inclusion, and equity. But to get to a point in a manufacturing or an industry or industrial organization where someone who doesn't have a heavy technology background or technology understanding gets to a point where they can be a successful leader, my advice would be, number one, make it about the customers. Learn your customers' problems, learn your customers' frustrations first and foremost, and that will lead you to the solutions that will help them overcome those problems and those challenges. Mm-hmm. And then when you're led to the solutions, do what you need to do to understand the basic technology. And when it comes to shareholders and understanding where profit margins come from and the profit that we have to run as a business and be successful, obviously we need to know how our customers can take advantage of our technology. But the changing business models of the technology, obviously, SaaS is becoming it's been a buzzword for a while, but it's going to become even more prolific in the future as business models have to change around technology. Yeah, and so I think that there's huge opportunity. Just speaking for myself, for those who don't necessarily have a technology background, to start around the people, the challenges, the solutions that can help them overcome the challenges, and then the business models that are going to provide the most profit and profit margins for those shareholders.